We will start out with the objective in terms of how we can design LLM applications. So from where we left off in the last session, we will carry forward and look at how we can design LLM applications for classification tasks and generation tasks. This is what we will see briefly in this part of the session. So I will take the example of a very simple exercise, which is sentiment analysis, and that is the general example that I will take to explain how this kind of a workflow is getting framed. So sentiment analysis is the use case where I give you a sentiment, I give you a particular review. Imagine you go to some e-commerce portal and you buy something, you go to Amazon and you buy something, you go to Flipkart and you buy something, and after that you write a review. So based on whatever you purchased, you write a review, and based on the review, the brands, the company brands or Amazon in this case, will try to predict what is the sentiment of your review. Okay, so let's say you buy some product or service and you're not happy with the product or service, or there's some defect in the product or service. You will go and contact Amazon support, or you will write a big email, big lengthy review email, and you will send it to Amazon support. So based on that email, the team will review what is the sentiment of that email. Okay, the team will review what is the sentiment of that email. Is the email positive sentiment? Is the email negative sentiment? And maybe if it is negative sentiment, Amazon will give you more priority or more preference, right? So they will try to resolve your issue faster because it's an escalation kind of thing. So that is the idea. That is the workflow that we are trying to create. And again, something I mentioned in the last session also, that classification tasks is not a new thing. This is something we've been doing for a long time. It is not that this is possible only with large language models. We already have traditional methods using which we could do something like this. So we are already able to solve classification tasks using methods like count vectorizer, bag of words model, word to vec models, and in the deep learning stack we can use RNNs, LSTMs to do this kind of sentiment analysis or basic classification. So these are all solved problems. We have been doing this for decades now. There's nothing new. But what we have seen is with large language models, because these are pre-trained models and because they are so powerful, we talked about that idea in the last session, like meta learning, remember, zero shot learning. Because they are so powerful models, because they have such a good rich understanding and context of things due to the zero shot learning capabilities, generally they tend to perform better in these tasks compared to the traditional architectures. And that is exactly the workflow that I'm presenting, how to build this kind of an application. So initially we'll have the whole data. The data is the complete data that you will have, which consists of the input output combinations, right? And remember, this is the traditional machine learning discussion that we were having in the last session. So how does the machine learn? How does the model learn? The model learns from the data that you provided. If you don't give the data, the model will not be able to learn. So machines also learn from the historical data. Machines learn from whatever data that you provide. So for the machine to understand that given a review, what is the sentiment, you will have to teach it first. You will have to teach the machine with lots and lots of labeled examples. So you will have to provide lots of examples like, okay, this is the review, this is the sentiment. This is the review, this is the sentiment. Let me write it down. Maybe that will be better to relate to. So, so what you can do, this is your data, and the data will be, you will have a review and you will have a sentiment, right? So I'll just write it this way. There'll be some X and there'll be some Y. There will be some X and there'll be some Y. So X is the review and Y is the sentiment. Okay. And this is the label data. This is the data that you will train your language model on. Not exactly training. This is again something called meta learning that happens. I told you already that LLMs are already pre-trained. You don't have to explicitly train it, but with some sample data, you can basically include these examples as part of your prompt. That is what I basically meant when I say training. So you will give the machine lots of this label data, review sentiment, review sentiment, review sentiment, so that the machine is kind of able to understand that given a particular review, what is the expected sentiment for your company. Something very similar to what I was showing you as an example yesterday. Yesterday, remember when I was discussing few shot prompting, I discussed the exact same use case. where I said that you will give the machine lots of labeled examples. Okay, lots of labeled examples. And that's exactly what we do. Okay, so you take the whole data and you keep aside a some percentage of your data for few shot. I'll call it few shot. And the other percentage of your data is gold example. This is like the test data. Usually the ratio is somewhat like this, 20%, 80%. I'm just giving a ballpark figure. Okay, so unlike traditional machine learning, where some of you would have worked on it, you're coming from that background. So traditional machine learning, we always do a 80-20 or a 90-10 split, right? So we actually try to take maximum amount of data for training and very minimal for testing. But in large language models, in LLM applications, it's kind of the reverse. We actually take a much more percentage of data for testing or gold and very few percentage of examples for few shot. Now, what is the reason? Because remember, here we don't have to train the LLM model from scratch because the LLM model is already pre-trained. It's a very powerful pre-trained model that we have. The large language model that we have right now is already a very powerful language model. It's already a pre-trained model, and we do not have to train it from scratch. We do not have to train that model from scratch. That's the idea. We don't have to train that LLM model. We don't have to train that language model from scratch. So that is why even with some examples, it will be able to learn. Even with few examples, it will be able to do very well. So that is the whole idea. So you take the whole data, you split the data into few shot and gold. So 20% of your data approximately is few shot. 80% is what we refer to as gold examples. And gold examples are like your test set. This is like your mock question paper. Okay, so this is what you will evaluate the model on. The format is exactly the same. Okay, here also you have something called X and Y. And here also you have something called X and Y. The format is not different at all. The format is the same. You have simply taken this data and split into 20% few shot. This is what you will use to kind of fine tune your LLM in terms of giving a good prompt. And this is what you will use to evaluate your prompt. Okay, so after the prompt is built, this is what you will use to evaluate. That okay, when the new review is this, what is the sentiment that the LLM is predicting? And now we will see the predicted sentiment with the actual gold sentiment. Gold examples are like the think of it like the final test data that you will evaluate the model on. So this is a bit of a new part that we are discussing now, how to evaluate a language model. All right. So these are your text label exemplars. Exemplars are nothing but the few short examples. There's another term called exemplars that we use, and this is how it will look like. So text is your X, and label is your Y. I think we are already clear on this. Okay. This is now going to be the text label exemplars. You will combine this with your system message. Mind you, there'll be a system message that you will have to also write, plus parameters, because there'll be prompt parameters like temperature, max tokens, top P, all that. Okay. And these are your few short examples. Okay. And what is the prompt now? The prompt is a combination of your system message plus your text label exemplars. So let's say there are two text label exemplars, U1A1 plus U2A2. This entire thing is basically part of the prompt. Okay. I hope everybody is able to get a sense of this. So you can see that when we design the final prompt is a combination of your design system message, whatever system message that you designed, and the few short examples. So in this case, I can opt to decide how many few short examples I take. So here, let's say if I take only two few short examples, two few short pairs, so then my entire prompt will look like system message plus U1A1 plus U2A2. And these two pairs of user assistant examples are basically used to give some kind of direction in terms of how the prompt should behave, how the LLM should behave. Okay, so this is what is used to fine tune the behavior using few short examples. Okay, so once this is done, that's your final prompt, and you will have a new user message, right? So this is how you design the prompt. Now the important part is there are a couple of variables here, right? There are a couple of variables here. The variables here are the system message itself, because there are different ways we can design the system message. The prompt parameters, there are different ways we can decide what values the prompt parameters should have. So we can set different values for the prompt parameters. And also, we can also decide what kind of text label exemplars we should have. Even this is a hyperparameter. You can also choose how many examples you should have. Should you have 2 examples, 3 examples, 5 examples? So you can decide how many examples you want to have. How many text level exemplars you want to have, you can actually choose that. So even that is the hyperparameter. You can decide how many examples you want to have effectively. So what you do is after you try out all the different things, you will, let's say you have a sample prompt. What you're seeing on your screen is a sample prompt. You have designed a system message. You have designed, let's say, two few short examples. You have decided what the values will be, and that's your prompt. And you have decided some parameters. So that's your complete prompt that you have. Now what you will do is you will evaluate the prompt. This is the most important part. Okay, you cannot build LLM applications if you do not evaluate. You will only be able to know the performance of your model if you evaluate your model on some unseen data, on some test data. And that is exactly what gold examples are meant for. Gold examples are meant to evaluate your model on unseen data, which is similar to a question paper. And you want to see how that model or how that application is performing on that question paper. So whatever prompt you designed, now you take the gold examples one by one. So this is like the X. Again, this is like the new user input. I'll call it U new. Okay, this is the new user input, which is the X. So you take the new user input, you combine that with the whatever the original system defined prompt that I had, which is the system message plus a few short examples. And now you take U new, that U new. And this is what becomes a final prompt. You make the API call. This is the API call. We did all this before. We can invoke the chat GPT, the GPT-4 Omni model, and the model will give a prediction. It will give a predicted label, and the predicted label will be what is the sentiment. Okay, it will give you some kind of a predicted Y. I'll call it YP. And now we will simply compare the YP with the Y actuals. Because remember, we already had the gold examples. We already knew the actual sentiment. So the actual sentiment is known. So now you take that new user query, like you take some sample review, and with that you make the LLM make a prediction. The LLM predicts that okay, the sentiment is positive or the sentiment is negative. This is YP, and now you simply compare the predicted sentiment with the actual sentiment, and that is how we get an accuracy score. Okay, so see how we can actually design a prompt. We can design a prompt, and when I say design a prompt, I mean to say design a system message, design your few short examples, design your prompt parameters. So design all of those things, and then you can evaluate the quality of your prompt. So after you design all those things, you can now evaluate the quality of your prompt. You can evaluate the quality of your prompt by measuring an accuracy score, and then you can try out different methods. So let's say you now try to change the system message. So now you decide, let's say you got an accuracy of 80%. I'm just giving a ballpark number, okay? Let's say you got an accuracy of 80% when you did this, okay? So you got an accuracy of 80% when you did this thing, okay? So now what you do, you change the system message. You make some tweaks. You make it a longer system message. Or let's say you try a different prompting technique like chain of thought prompting. We talked about COT prompting in the last session. So you do something called COT prompting. You try to incorporate more details in the prompt. You try to make it extremely detailed, extremely methodical, step by step, reasoning based instructions you're giving. You change the system message completely. You change the prompt parameters. Let's say increase the temperature value a little. Okay, so make it a bit more variable. Outputs to make it a bit more variable. Okay, let's say you change some other settings. Okay, you change some other parameters in the thing. And also you try to incorporate more few short examples. You give more examples, not just U1, A1, U2, A2, not just 2 pairs, but you give, let's say, 7 pairs. Because the more examples you give, the more data the language model has to tune itself. The more variety it is seen. So more data is always good. Not always, not all the time. You need to have too much data, but more data is definitely generally always good. So the more few short examples you give generally, it will be able to fine tune better. So let's say in the next iteration, I give more few short examples, better system message, better parameters. And now I use that to do the prediction. When I give a new user input, the model will predict some sentiment. And this time, the predicted sentiment is very close to the actual sentiment. And you are getting, let's say, close to 99% accuracy. So this is how you compare prompt templates. This is basically what we are trying to do when we are designing applications. So we try out different templates. We try out different methods. And then we have some kind of a gold example or some kind of a test set, which we evaluate our language model applications against. And if we get a high accuracy, that's the solution that we take. This is the approach that we generally follow. And this is what we do for the classification task. So the slide is very simple. There is not much that is going on here, but this is a generic approach that we'll follow for all our classification exercises. So if you see the way we will break down the session now, so we'll see a demo, we'll see an example, and uh, and then we will see a very similar approach even for generation tasks. Okay, so now with this in mind, I hope everyone is clear on this one. So now with this in mind, let us see one application in terms of how to implement this in code. Because once we see a small demo, it will be a lot more clearer as to what is going on. So we have the classification tasks folder, and I'll quickly show you a small demo from there. And the demo is exactly based on sentiment analysis. It's not something very different. We have the same sentiment analysis folder here also. Initial part are a couple of pip installs that you are required to do. So first we need to do a pip install of datasets, and don't worry too much about these things. So datasets is basically a Hugging Face library. We introduced something called Hugging Face yesterday. Hugging Face is a very popular open source community of data scientists, machine learning engineers, GenAI developers. So anything and everything to do with AI and data. So that entire community, Hugging Face is one of the biggest communities out there. So a lot of people contribute data sets, models, everything there. So we actually have a Python package for that as well. So we can download data sets, pip install data sets, and this way we can actually take data right from Hugging Face. Can you see? It's actually getting installed. So now we can do the rest of the stuff. We already did part of this in yesterday's session. You are already able to install the secrets yesterday, and whatever secrets you installed yesterday will already show up. You do not have to do this today again. Okay, so you already did the secrets part yesterday, Azure API key and all this. So this is the same collab, this is the same account that you're using, right? So against the same collab, against the same account, this will come up. There'll be no difference here, right? So I will just load the API key. The endpoint URL and all this is the same. Okay, this is all the same, right? This will not change. This is for me, but for you, remember, you will have to change your endpoint URL, and you already know how to do it. You already know that you can go to view code, you can take the endpoint URL, and you can modify it. Okay, so this is just one thing you need to keep in mind. Just make sure in all these notebooks that I share, you just go and modify your endpoint URL. Okay, so this is just a basic initial setup that I'm doing. Rest, there is nothing much to talk about. This is the same workflow that I discussed already. And now we will just see a simple code example of the same. So first, let me show you the data. What type of data do we have here? Right? I'm taking a simple Amazon use case, and this is my data. This is my data. All of you can see. So we have the content and we have the label. The content is nothing but the actual review. This is a long review a customer has written. So the content is a long review the customer has written, and the label is basically the sentiment. Is it positive? Is it negative? Is it positive? Is it negative? That's the idea. Okay. And you can see it's obvious that the zero means sentiment is negative, because I think the third review is talking about problems. The user was not happy about the purchase. The third review talks about problems. So the sentiment is kind of negative for the third review, whereas the fourth review, the sentiment is kind of positive, because the label is one. I think the user was very happy about it. Okay, so we already have this data, and see how we already have kind of split our data into training and a few shot and gold examples. This is already done, right? So it's already done. So we've already split our data into few shot and gold examples. And here we have actually split equally, although in a more real world application, the split will not be equal. So as I told you, you will have a very small percentage of data for few shot, and like majority of your data will be part of gold, because gold is very important. LLM application evaluation is the most important part. You need to keep a substantial amount of data aside for evaluating the LLM models, how they are performing. Okay, so here it is already done. You can see the split is already done here. So we have something called example reviews, review examples DF and review gold examples DF. DF is nothing but data frame. Okay, so now that is done. So this is a simple prompt that we have right now. The system message: classify product reviews in the input as positive or negative based on sentiment. Do not explain your answer. Your answer should only contain the label 1 positive or 0 negative. You can see how we are explicitly stating that given the review, please output either this or this. Do not explain your answer. Don't explain the reason why you gave me something. Just output, either it is positive or it is negative. That is all we want to see. We just want to see the output, nothing else. You're explicitly specifying that. You're explicitly stating that. Okay, and now we are actually curating the, so we are actually curating this thing. We are curating the examples now. This is a bit of Python that we are doing. So again, I mean, so all that we are doing is we are basically appending the few shot prompt. So you can see we are taking a sample of 4. So all that we are doing is we are basically assembling a few shot prompt with 4 examples. So that is all that we are doing. Okay, we are assembling the few shot prompt with 4 examples. This is just a little bit of Python code that we've written where you can see we already have something called Amazon reviews examples DF. So we're iterating through all the rows. We are going through all the rows of my data frame, and we are appending the user and the assistant examples. So we already have this, right? So we are simply curating the prompt this way. Maybe if I show you the output, it will be a lot clearer. If you see the output, this is what we curated. So we went through all the 4 rows, and we took actually sample of 4. That's why we created 4 pairs. Okay, if you want to see the 4 pairs right now, what are the 4 pairs? User assistant, user assistant, user assistant, user assistant. So can you see the 4 pairs that we got? These are the 4 pairs that we got. Okay, so this is the first user assistant pair, UA. This is the second user assistant pair, UA. This is the third user assistant pair, UA. And this is the fourth user assistant pair, UA. So these are the 4 few shot examples that we have. And at the top, you can see the system message. So this is what I was talking about. This is what you curate. This is part of your prompt design. And this is just iteration 1. Now, let's say with this prompt, I will query the LLM model and I will see what kind of predictions it is giving on the new data. I will evaluate the model. And let's say if I'm not happy, what I will do is I will go and change the system message. I will go and take more number of sample examples. Let's say in this case, I will take 8. I'll take more number of sample examples. And then if you take 8, you will get a bigger prompt. Can you see? If I take 8, I'm actually getting like 8 few short pairs. So this is something that you have to try out. You have to iterate and you have to try out. You have to try out different examples and see what works generally. Okay, actually, this is adding on top of it. So I need to first go and kind of take the few shot and do it again. Okay, yep. I think I initialize a variable somewhere here. It's actually a list, right? So anyways, let me just do it from the top. Yeah, it's a list. So because I'm appending, so it will actually start from here. So I had to actually, because this is a list. So when I do append, it is just adding on. So even if you change it to sample 4, sample 8 is simply the appending to a list. So you have to run this code again. You have to run from here again, and then it will work fine. You can see I'm back to the 4 few shot examples which we originally did. Okay, and now we will look at LLM evaluation. So we have predictions and ground truths. Predictions are basically the predicted sentiments, and ground truths are basically the gold examples. What are the actual sentiments, the gold examples? Okay, so straightforward, and we can let the model work. I'm not taking you line by line through the Python code because I mean this is all basic Python. So you can see what we are doing is we are going exactly what I explained in the theory. So now you're going through every single row of the gold example, and you're taking a new user input. This is the part where you take a new user input. See, this is the gold review. So you take the gold review, which is nothing but the user input. And now inside the try catch block, you are actually doing a chat completion create. So you already have the few shot prompt. And on top of the few shot prompt, you add your new user input. You add your gold user input. And based on that, you get a predicted response. The response is nothing but the predicted response. And this you continue appending to the predictions list. And and at the end, what you do is you go and compare the predictions list with the ground truths list, and you get an accuracy score. This is all that we are doing. This is take a little time because remember we have a lot of text. We have a lot of text, and at the end of it all, you will see an accuracy score. And after you get an accuracy score, what you can then do, you can go back to the system message, you can modify your system message a little, and then you can again come back down and you can see the accuracy score. And this is how you will iterate. This is actually what prompt engineers will do. The next time when we hear the term prompt engineering, a lot of people get confused. Okay, what are they really doing? This is the kind of work they're doing. They're trying to modify the system message. Because remember, in the front end application, when you're using any front end application, even something like Chat GPT, which is so ubiquitous now, it's so common in every household now. Okay, it's a household name today. Everybody knows it, right? So we have no idea what the prompts are. We have no idea what the system message or the prompt template looks like. We have no idea. We are only giving the user inputs. Okay, but the makers of ChatGPT, they would have spent a lot of time. They would have tried different system messages. They would have also given some few short examples, which we have no idea. We have no idea what kind of parameters and everything they have given. So they would have also uh, done a lot of these customizations, and they would have evaluated their prompts, and they would have deployed the final one. Okay, that's the idea. Very interesting. You're also getting an error code. You can see 400. 400 is an error code which says uh, this is actually fine. This won't, the system will not error out because it's a try-catch block. So maybe there was some review that got errored out due to the content management policy. And if you just see, this is one of those reviews that got errored out. You can see which part where the error happened. You can see content filter was triggered, and which part of the content filter was triggered? Hate? No, this was not triggered. Filtered false. Jailbreak? Filtered false. Jailbreak was not triggered. Self-harm filtered false, and maybe sexual is filtered true. So maybe this was some abusive comment or something people wrote. You know, let's say you purchase something on Amazon and you write some abusive comment. So this is the content management thing that was triggered. Okay, but because we are in a try-catch block, only that row will be ignored, and the rest of the records will be processed. Okay, so this is another very interesting thing that you can see. You can actually go and see step by step which of the records are getting ignored. Okay, yeah. Anyways, for the rest of the predictions will work fine. So every new user input is going through the API. We are getting a predicted sentiment, and now we will compare the predicted sentiment with the actual sentiment. And if we get a high score, we can be confident that yes, our prompt is good. We have designed a good quality prompt, which is ready to deploy. We'll just wait for this to complete in a minute. Let's see, because you have to understand the context. Like the number of tokens is massive. So the moment you start building applications at this scale, and we'll see a big part of this today also, you'll start to see the amount of token counts is huge. You're talking easily about crossing 1,000 to 10,000 tokens now, because there's a lot of text. Every review is very big actually. If you just open it up and see in detail, that's why it's taking time. And it is complete now, and you can see we're getting a 96.774% accuracy, which is quite good. 96.774% accuracy we are getting, which is a pretty good number that we are getting right now. Okay, and now you can, what is iteration two, what you can now try to do is we can go back and make some modifications in the prompt, and we can again run it, and this is how we can test out our prompt templates. Okay, and if you come all the way down, what we have done is something called a classification report. Now this is again some people who are coming slightly from a traditional AI and machine learning background can relate to it. So not only can you get the full score, but you can also go back and in a way uh, find out the class level performance. You can also build something called the confusion matrix. You can see, okay, what is the performance of only the negative class, and what is the performance of only the positive class. So you can look at things like false positives, false negatives, true positives, true negatives, and you can see the class level performance, right? So at a very high level, I'm not getting too much into the theory of all this right now, but at a very high level, you can think of using something called an F1 score, and you can look at the class level accuracy. So here the overall accuracy is 97%, which is anyways very good. But not only can we see the overall accuracy, but we can also see the class level accuracy. This is like a weighted accuracy. F1 score is like a harmonic mean of precision and recall. But anyways, at a very high level, you can use an F1 score to gauge the overall quality of the model on an average, right? So you can see the class level performance. And why it is important is because, see, here it doesn't, like, maybe it's not that useful because we only have two classes, either it's negative or it's positive. But then if you have a multi-class classification, if there are multiple categories, Like, let's say typically for a document management system that a lot of enterprises are using, you might have a very, very real world classification task. So you are having a lot of document data, and based on an automated system, you want to categorize documents into different types. Okay, so let's say based on the text of the document or based on the title of the document, you want to categorize the documents into different types. And you have 10 different document types. Okay, type 1, type 2, type 3, type 4, up to type 10. Okay, or it could be also related to support tickets. So you've got 10 different classes of support tickets that the support ticket can be classified into. So based on the ticket message, based on the support ticket message, you want to classify what category the support ticket belongs to. Is it a category 1? Is it category 2? Is it category 3? Is it category 10? So that's the problem that you're trying to solve, let's say. And there you will have an overall accuracy that is fine. But what will be also very important to see is what is the individual class level accuracy. You also want to know that how is the model performing with respect to each of the types. So I want all the types to do equally well. I don't want type 1 to do like 100%, but type 2 to be like only 10%. That is useless. So the classification report gives you a very strong understanding in terms of how individual classes are performing, not just the overall how it is performing, but also how the individual classes are performing. And that can also help you in debugging, and then you can do a root cause analysis and all those things specifically with respect to that class. So if you see, let's say the type 2 type of documents are not getting categorized correctly, let's say the accuracy is coming out to be around 10%, the F1 score is around 10%, let's say, then what you can do is you can now explicitly look at the type 2. What is going wrong? Why is the language model unable to categorize the type 2 documents correctly? What is going wrong? Maybe it could be that, okay, type 2 is very similar to type 4. Maybe the text in type 2 is very similar to type 4, something like that. Maybe there are two products that your company is using which are very similar. So the LLM model is unable to differentiate between what is type 2 and what is type 4. So that's why a lot of mistakes are happening, a lot of false positives are happening. Okay, so and these are very, very good ways to kind of figure out. And maybe if that happens, maybe the next step could be you can combine type 2 and type 4 together. So no need to have them as separate categories. So maybe at the company you decide that, okay, we don't need to have 10 different document categories anymore. So because type 2 and type 4 are getting confused because they are so similar, because these two products are very similar, uh, we don't need to have separate categories for type 2 and type 4. Let's club them together and call it type 2 4, whatever, something like that, type 2 4 combined. All right. So this is demo number 1. Demo number 2 is also very interesting. I'll just quickly complete this second demo and then we can do one exercise. Demo number 2 is very interesting because it's an aspect-based sentiment analysis. And here, what we are trying to do is we are trying to look at not only to predict the sentiment, but we are also trying to predict the aspect. So we are trying to do two things here. We are trying to predict the sentiment and also the aspect. The aspect and also the corresponding sentiment behind that aspect. Okay. So what am I trying to say? Let me take it up with all of you. Let's say for an example, so what I've done is I've taken it to Amazon and let me just randomly look up a phone here. So I'm just looking up S25 Ultra. That's an example. And if I quickly take you to this phone, for all these mobile phones, you will see there's a review section. So a lot of customers will buy and they will give go to the review section. There's something very interesting, right? So what Amazon will do is they're doing two things. One, they are actually trying to give customers are trying to give an overall review. And customers are also writing comments, right? So when you go and do a review on Amazon, you have to write a text and then you will give a 5-star or a 4-star, whatever. Now, the interesting part is if you look at this person, Nihir Shah, okay, what is Nihir Shah saying? What is Nihir Shah saying? Let's see. Okay, maybe Nihir's, let me look at negative reviews. Maybe that will be better to see, like, let's see. So we have a person named Lakshmi. So Lakshmi is saying, I'm writing this review after 3 months of usage. In my 3 months, my device power button is not working properly. Okay, so what are the aspects that Lakshmi is talking about? So Lakshmi is talking about the power button, some kind of hardware issue. While using, I'm not feeling it like Samsung Galaxy 25. It is like a first copy mobile. I think in India, Samsung is manufacturing cheap mobile for Indian customers. Okay, well, I don't think there's much we can take. So anyways, so what is coming out of this? Two things. One is from the review, we are trying to find out what is the aspect the customer is talking about. So the customer is talking about the build quality or the hardware. Maybe there are two aspects the customer is talking about. One is the hardware. Second is the build quality. The build quality, because somewhere they say, cheap mobiles, whatever, build quality. So you identify what are the aspects the customer is talking about. That is the first part. And the second part is for every aspect, what is the sentiment? I think this customer is negative all through. Okay. The customer is negative all through. Lakshmi would have been happier if the same phone was given in 10,000 rupees. No? Anyways, if you're paying so high for a phone, then you want it to be good quality. So now let's look at one more. Let's look at one more example. Let's look at one more example. I think something very good about the phone. Maybe he was paid by Samsung, right? There are a lot of these sponsored reviews, right? Anyways, so Nisha, right? So Nihir Shah has written that, okay, design and display. Okay, I think he's very explicit here. So we can take a slightly more generic example. Look at this one. Look at Kushagra. Kushagra is saying the design, look and feel, AI functionality is top notch. So in this review, what are the different aspects that Kushagra is talking about? So Kushagra is talking about the build quality, the battery, the display, and the software. Because multitasking and AI is part of software. So the aspects that Kushagra is talking about is hardware, software, battery, and display. Straightforward. Actually, he's talking about everything. Okay, so maybe uh, what comes out of this is the hardware or the build quality. So Kushagra is saying the build quality. So from the review, you identify the aspect is build quality, and the build quality is 5 star, and he says pretty good too. So he's not that happy. Let's say S Pen support. S Pen is one of the other aspect, and he's kind of like, let's say, 4 star. Okay, gaming experience. What is the other aspect that Kushagra has talked about? So Kushagra is talking about gaming experience. They say that is 4 star, something like that. So you get the idea what I mean by aspect-based sentiment analysis. So here, based on a review, first step is you try to identify what are the topics or what are the aspects that are being talked about. What are the different things that are being talked about with respect to the review? And then for each and every aspect, what is the sentiment for that particular aspect? Okay, so it's a very powerful, way of evaluating reviews, not just giving a total sentiment score, but looking at every aspect and aligning the sentiment scores. And the other exciting part is Amazon is already using it. And they would have gone through all these reviews across all the hundreds of customers, and they've reviewed it. And what Amazon has done, this is a very good use case of Gen AI. Amazon has basically gone and summarized it. So they would have taken all the reviews, but something very similar to that meeting transcript, no? So we have like what? Uh, the entire meeting lasted for like 7 hours, right? We would have easily generated upwards of 100,000 tokens, or maybe close to 10,000, 100,000 tokens, more than that. And we would have summarized all of that within, let's say, 100 words. That is what it is. So by going through all the reviews, Amazon has summarized it. That is part number one. Part number two, for every review, it would have identified what are the aspects. I told you, right? And here they have simply summarized the aspects. Can you see? These are the different aspects that they have summarized. So camera quality, battery life, performance. And now you can click on each and every aspect. And I told you for every aspect, there's a sentiment assigned. And now you can click on each and every aspect. Let's say something like camera quality. And you can see that in terms of camera quality, how many positive, how many negative. This is aspect-based sentiment analysis. Because we know that every review, which are the reviews that are talking about camera quality, and with respect to camera quality, how are those customers feeling? Not just the overall feedback, but what we want to know is specifically with respect to that category, how are they feeling? Right. So this is a very powerful way of evaluating and collecting feedback. So if you look at it historically, this was not possible. Historically, we used to give a long questionnaire, no? Like if you want to collect feedback about the product, what you will say, you will send a form to a customer and you will ask the customer to rate. Okay, like camera quality, how much rating you give, battery life, how much rating you give, performance, how much rating you give, right? But here what we are saying is you just write one text, you just write one review, and from that we will figure out how you feel about it. right? Even all these session feedbacks also, like let's say, all these sessions that we do, let's say there'll be some feedback mechanism at the end of it. So there also you will be asked, right? So here we still are sticking to the same traditional methods, right? So you will have to rate, okay, how was the delivery, how engaging was it, right? You will have to rate on different parameters, right? So let's say there'll be 5 to 10 different parameters and you have to rate as an example. But the beautiful thing is, imagine you just had to write one review. Just write one review. Don't have to go and rate on every parameter. Just write your review. And based on your review, we will identify what are the aspects that are talked about. And the model will be able to automatically find out the ratings for each of the aspects. So you just write 100-word review. And from that 100-word review, the model will identify, okay, based on the session engagement, the review is this. Based on the contents covered, the review is this. Based on the delivery style, the review is this. So that is the idea. That is the aspect-based sentiment analysis. And these are some very new things that are actually starting to happen. And you can see that the animation speed. Not many people talked about it actually. Very interesting. Only 3 customers talked about it. The only 3 customers mentioned animation speed actually. And value for money, you can see. Not many people feel is value for money. Speed, battery life, performance, and all that. AI functionality. Remember, there was a review where AI functionality was there. I'm not saying that this is perfect. Maybe Amazon also has to do some work, right? So this is not perfect. There could have been other things that they could have also included, right? Maybe S Pen and all that. That's not there. So maybe there could be more aspects. So maybe that's another thing we need to keep in mind that this is not perfect. Amazon is also, trying out different approaches to make their model better. So just by looking at it, you will realize that this is not perfect. So they've included something like animation speed. So out of 162 customer ratings, only 3 mentioned it. So this is not very useful, right? If you look at it, this animation speed is not very useful to put it. Rather, there are other things that were more important. Like camera battery life is fine, performance is okay, but I think generally what customers also look for is, let's say, charging. I'm just giving an example. Okay, battery life is there, but there could be some other things like, let's say, functionality. Here it's a very broad thing like AI functionality. Only 4 customers talked about it, but maybe a better aspect could have been uh, something like software. General software, general software and performance and UI and all that. That mention is not there. But actually we saw a lot of reviews that talk about it. No, I think there was a lot of reviews that actually talked about this thing. See, I mean, this thing like S25 Ultra is very snappy, apps open instantly, higher refresh rate. So this is what we want to see. But somehow this aspect was not captured. So maybe this is bad development on Amazon's part. Whatever. I mean, this they will iterate and they will make it better. So maybe a better aspect here could have been, okay, something like not animation speed, because only 3 customers talk about it, not animation speed, but you can probably group animation speed and AI functionality into one broader aspect, which is, let's say, something like software quality. How is the UI? How is the overall UI? We are talking, I think now they have Galaxy has launched the One UI 7. How is the overall UI generally? Okay, so now moving on to the implementation. This is not very hard. You can all try this out later on, but I'll let me run this for you and show you. This is the sample example, and this time it's a JSON file that I've got here. Okay, the same kind of aspect-based sentiment analysis, but we have to give some examples, right? I told you that to build an application, we have to give some few short examples to the model. So here we are giving some few short examples also to the LLM. So we are also giving some few short examples here. And these are the few short examples that we are providing. You can see. So the sake menu should not be overlooked. So what is the aspect that is being talked about? It is sake menu, which is something to do with food. And the polarity is positive, right? Great spot, whether looking for a couple of drinks or a quiet dinner. So this is the general review that somebody has written. Okay, after maybe they went some restaurant. This is the restaurant review, it seems like. Okay, and what are the aspects that are being talked about here? Because we have to, this is the label data, right? This is the few short example. Ultimately, in a real world scenario, we want the model to predict what are the aspects. But here we are giving the few short examples so that we are guiding, we are training the model. So based on the review, the few short aspects are, the aspects that are identified here are drinks, dinner, and spot. Maybe you can broadly call it ambience, whatever. Drinks, dinner, and spot. Okay, and this can be broadly categorized as ambience. Okay, and the polarity is positive. So identify the aspects, and for each of the aspects, the polarity is positive, positive, positive. Okay, so this is the general idea, but the approach is very similar. You can design the prompt. You can see we are writing a very detailed system message. And in the system message, we are very clearly stating that what are the different aspects that are possible. Okay, so in each review, there might be one or more of the following aspects: food, service, ambience, or anecdotes, miscellaneous. For each review, identify presenters' input, identify if there are any of the four aspects, and assign a sentiment polarity for each aspect. So we are explicitly guiding the LLM that, okay, first you do this, first you identify what are the aspects. And the review can have multiple aspects also, we know that. And once you have identified the aspects, for every aspect, you please find out what are the, uh, excuse me, for every aspect, you find out what are the sentiments with respect to that aspect. That's the way we do it. Rest is very similar. We will curate the few short prompt. And you can again see that we have used a sample of 4. If you want to change it, you can, but we have only taken one with 4 examples. This is the default one that we have taken. And this is the final few short prompt that we are getting. So there's a system message, user assistant, user assistant, user assistant, user assistant. This is done. And now we will come to prompt evaluation. Very similar to what we talked about. And we can first give the gold examples, and we can get the predicted aspects and predicted sentiments. And here we can compute the accuracy. The accuracy will be lower. You can see it's coming around 65% is lower. And this is expected because it's a harder problem. I mean, just in first glance, in case you're having the question, why is the accuracy low? Because it's a little more difficult compared to a simple sentiment analysis. It's a little more difficult because, mind you, you have to get both right. You have to get the aspects right, and you have to get the sentiments right. Both the things have to be correct. Okay, both the things have to be correct. The aspects have to be identified correctly, and for those aspects, the sentiment has to be identified correctly. So both has to be correctly done. So based on a review, you need to correctly identify what are the aspects of the review, and you need to correctly identify what are the sentiments of those respective aspects. So both need to be correctly done. So you can see the example very nicely put actually. You can see the ground truth. This is the ground truth. That means this is like the gold example. Let's say there is one review, review 1, and for that review 1, the actual aspects are aspect 1, 2, 3 in that order. And for every aspect, the sentiments are positive, positive, negative in that order. This is the ground truth. This is what we expect. Right? So this is the ground truth. This is what we expect generally. This is what is expected generally. This is what we expect. Now the thing is, the first set of predictions, if you see, review 1, aspects are correctly identified and sentiments are also correct. This is a correct prediction. A correct prediction is one where everything is correct. The whole thing is correctly done. That is a correct prediction. The second one, if you see, is not correct. Why? Because although the aspects are identified, 1, 2, 3 in that order, this is matching, but the sentiment is not correct, not matching. So this is the incorrect prediction. This is straight away 0. Even the third one is not correct. Why? Because not all the aspects are identified correctly. So the model has only identified one aspect. So this is also incorrect. We can debate over it. I mean, if you're building a real application, you can debate over it. You can maybe give a weighted rating, weighted average you can do. Maybe you can consider some part, or if you want to consider some part of the answer, you can also do that. Give a kind of a weightage. But that is the reason why the accuracy is coming out to be low. It's still running right now, but it has to get everything right. It has to get the aspects right, and it has to get the sentiments right. It's a harder problem. And what are the ways you can make it better? You can actually write a better system message. You can show it more examples. If you see right now, I'm only showing it 4 few short examples. Maybe 4 few short examples is not enough. Yes, the large language model is a very powerful pre-trained model. And we talked about meta learning in the last session. It has a lot of very good zero-shot capabilities. It understands things very well. But maybe still, if you show it some more examples, it will do better. If you have some more exemplars, some more few short exemplars, if you can show it, it will still do better. So these are some of the things that you can try out by modifying the prompts. Okay, I will wait for it to run. And this is the part where I will encourage each one of you to also, oh yeah, I think it's now completed. It's now completed. And now let me see the score. You can see 62.5%. Okay, so as I told you, accuracy is very, very low right now. Okay, accuracy is very, very low right now. And now at this point in time, I will encourage each one of you to also just try this example. Just try this example and see what you're getting. And the overall exercise that we will do now is very similar to that last use case that we discussed. So we already talked about the classification tasks thing. This was the sentiment analysis and the aspect-based sentiment analysis that we saw. And we all understood the workflow well. We all understood exactly how the workflow will have to be constructed. So we take the data, we split the data into examples and gold examples, and we curate the prompt, and then we test that prompt against the gold examples, right? And we get a predicted label, we compare with the actual labels, and we get an accuracy. And we also talked about the confusion matrix and other things. And based on that, this is the new exercise that we will be solving, patent abstract classification exercise. So let me quickly take you through the solutioning, how we are attempting this. Very similar. All that I did is I just went ahead and changed the file name. You can see pip install datasets is where we will take the datasets from Hugging Face. And this is how my dataset looks like. So you can see that every row corresponds to a text and a label. The label is basically the under what group the patent is grouped into. Very much like a document categorization, or maybe another real world use case could be how we go and categorize news stories, something very similar to that. Okay, so you look at a use case like Google News. So you've got different types of news story, and based on the different types of news story, based on the content of the news story, you're effectively trying to classify what is the so based on the different you know uh, category of the news story, you're trying to classify what is the class of that particular news story. So that's the use case. So something very similar we are trying to do. Okay. So again, we have the how many different classes we have. You can see we can use something called value counts to test that out. 1, 2, 3, 4, 5, 6, 7, 8. So this is the multi-class classification. Unlike the last use case where we had sentiment analysis, it was binary classification. This one will be multi-class classification. Okay, so multi-class means there are multiple categories that we have right now. So we are looking at something like a multi-class classification here. Okay, and we'll try to uh, identify from these categories. Okay. One more very important aspect I wanted to talk about is it's very important to ensure that you have the right quality of data. It's very important to ensure that the data quality has to be good, the data quality has to be strong. And I think if you just look at this current exercise, the kind of data that is given, the data doesn't seem to be very well organized and well balanced, because there seems to be lots of examples of human necessities, but there are very few examples of fixed constructions. And this is an important thing I wanted to clarify. So you need to have a well balanced data. So don't have like lots of examples of one category and very few examples of the other category. Okay, so we need to ensure our data is well balanced, and this way you'll be able to give you'll be able to curate a better quality prompt. Because remember, all this is going to be part of my few short examples, right? All this will be part of my few short examples, what I will use to fine tune my prompt. Okay, so it is like saying that you're showing the LLM model more examples of human necessities category, but very few examples of fixed construction category. Okay, you're showing the language model more examples of the physics category, but you're showing it very less examples of the fixed constructions category, and that is a problem. So when we talk about fine tuning, when we talk about fine tuning the language model, or fine tuning the prompt in this case, right, through a few short examples, uh, maybe the LLM will not learn human necessities, fixed constructions very well, but it will learn human necessities very well, because there are lots of examples that you're giving for that. So data curation is a very, very important part, goes without saying. It was true in traditional machine learning, and it's so much true even in generative AI based tasks also. It's very important to curate the data, fine tune the data properly. So all these are very risks we have even today. Okay. Okay, moving on. What we have done is, again, we have split our data into few short and gold examples. So, and you can see here in this exercise, I'm actually trying out different types of prompting techniques. As I told you, this is something that needs to be tried out. We have to try out different types of prompting techniques and see which one works. So first, we try out a zero-shot prompting technique. You can see this is the system message, and we are very explicitly stating that what are the different categories that you have to group your patent abstract into. So depending on the patent text, these are the total 8 different categories. There are 8, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 different categories we have to group it into. Okay, I'll give you a slightly better suggestion. Instead of directly listing out the text, because each of these categories are fixed, right? Another very good practice that we use for classification problems is we try to label encode these texts. We don't explicitly say that, okay, group as part of this category, group as part of that category. We don't do that. We don't explicitly state the text of the category. But another very real world way how we do it is we just encode it with a label. We encode it with some kind of a label, and we say, okay, let's say human necessities is part of label 0. This is label 1, 2, 3, 4, 5, 6, 7, 8, 7. So instead of saying human necessities, we will call it 0. Instead of saying physics, we will call it 1. Just like how we were doing the sentiment analysis. Remember, we had sentiment 0 and sentiment 1. 0 means negative, 1 is positive. So something very similar we will do here also. So we will label encode these outputs. What is the benefit? The benefit will be to some extent with respect to accuracy, because remember, they are language models, and the more text you have, on one hand, there's a token cost that you're incurring. So if you ask the language model to generate that entire token, there's a higher costing. No, we don't have to print out. Like for example, here, mechanical engineering, lighting, heating, weapons, and blasting. We don't have to print out all these words, right? We're already adding close to approximately 6 to 7 tokens here, but we don't need that. If we can replace this entire thing with a single label, let's say label 6, I just want the language model to print 6. That's it. And 6 corresponds to this. We can maintain a separate dictionary, in Python, where we can say, okay, 6 corresponds to this particular label. And then we can separately output it later. But we want the LLM to only print 6. Okay, so we can label encode. This is again a best practice that we use. So for the current exercise, the solution that I've shared, I just stuck to the normal approach, where I'm asking the language model to list them into these corresponding categories. You can see. So these are the corresponding categories that we are having. And then we try out some other variants of prompt. This is one more very detailed prompting that we are trying out. You can see. Again, each abstract can belong to only one of the following categories. And the only additional thing we are doing here is we are giving a more detailed description of each category. And why is it important? Because remember that, yes, the language model has few shot capabilities. We are not denying that. We are absolutely clear with the fact that, yes, all these language models, they have few shot capabilities. They have an inherent understanding of things. But you are still adding some more detail to it to help it, to guide it, that what is human necessities, what is physics, what is electricity, what is general tagging, because you are the domain expert, right? This is your field of work. The LLM is trained on generic data, yes, but that's an assumption that you're making. You are trying to ensure that it is able to correctly classify, and it is able to correctly classify the text into the corresponding categories. So that is one of the things that you're doing here. Okay, so the more detail you add, the better the quality of the prompts. You can see all that I'm trying to do here is I'm just trying to try out different system messages. This is system message variant 1, variant 2, variant 3. You can see the solution file also, variant 4. Okay, and this is something called COT with thinking exposed. Okay, and what we do here is right at the end we say, present a detailed description of your thinking process. It's a chain of thought with thinking. So this is especially very useful, especially when the LLM makes some mistakes. When the language model makes some mistakes, you want to go back and see at what mistakes are made and why those mistakes are made. So this is with thinking exposed. That's what we are actually tracking here. Okay, and if you scroll down, this is an example of a few short prompt. Same thing, we have the detailed system message, and this is how we are curating the few short prompt, exactly like we did for the sentiment analysis use case. And you can see here I'm taking 4 examples, and you can vary that. I told you already, especially very important for this exercise, because this exercise there are 8 different unique categories, right? And because there are 8 different unique categories, what will happen if you take only 4 few short examples? Maybe there are some categories that might get missed out. Okay, there are some categories that will get missed out. So if you take only sample of 4, remember there was only one example of constructions. There was only one example of some of the other categories. If you take only few short examples of 4 samples, if you take in few short, some of those categories can completely get missed out. And that is the problem. So this is again goes to show that why it is important to iterate and try out different things. Okay, so take a higher sample size here, because there are 8 unique categories. So at least the sample should be at least 8. I'm saying at least. and more than that, maybe you can take 16 or 32 in this case. And you have to also ensure that there is an equal balance of the different classes in that sample. Okay, so there should be equal number of human necessities, there should be equal number of fixed construction, equal number of physics. Ideally, we should have a very well balanced data set to start with, because otherwise what will happen is the LLM will end up becoming biased. So if you show it more examples of fixed construction and less examples of physics, then it will learn the fixed construction part well, but it may not learn the physics part well because it has not seen enough examples of how it is done generally. Okay, so this is very important, and you can already see the few short prompt is a very, very big prompt. Okay, and this is again part of your system message and few short. I think now everyone's getting a slightly better understanding, in terms of what is this system parameters, what is it that you're actually developing. So what you're developing is this: you're developing the system message, you're crafting a detailed system message, you're curating your data properly, you're crafting a good amount of few short examples, well balanced examples, and at the end of it all, you're crafting a high quality prompt along with high quality prompt parameters. And once you have that, now we will test it out. We will test out that prompt against the ground truth data, and we are getting 37.5% accuracy. This is not surprising because remember I told you that this is not a well balanced sample I've taken. So the data itself was flawed, and also the few shot prompt I've taken is flawed, because in the few shot I've only taken, if you remember, a sample size of 4, which is not even covering all the categories. Okay, so these are very real problems that I wanted to highlight in this particular exercise. Okay, and then rest of it, at the bottom, I'm actually going and correcting some of the things you can see. Okay, so we are just trying out some more variations right now. So here I've tried a sample size of 20. The sample size of 20, just having a higher sample size itself is not going to solve the problem, because remember, my inherent data is still imbalanced. So you'll have to correct that imbalance first. And maybe here also it's randomly taken. When I say sample 20 means out of the whole data, 20 rows are randomly taken. So you have no control on what classes are getting selected, what classes are not getting selected. Okay, so this is also very, very important. And in this particular exercise, the classification report will be very, very crucial for you. So although we are getting 34.75% accuracy, this is the overall accuracy that we are getting. But what will be particularly interesting to see here will be the classification report. Okay, so but yeah, I mean, if you try to run this prompt, it will take a long time, because I think that few short prompt easily will cross upwards of 10,000 tokens. It will be a long prompt. Okay, it will take more time in this case, but it will be very interesting to see the confusion matrix and the classification report, and you will actually get to see the class-wise accuracies, the class-wise F1 scores. Okay, how every class is performing, not just an overall 37.5% accuracy, but each individual class, how is it performing? And you will see very clearly that some of those classes, like if you remember fixed construction, like we had only one example of that, right? So whichever classes had only few number of examples and which are not represented well in the whole data, so they perform very poorly. So they perform very poorly, and maybe for those classes, the model will perform very poorly. Okay, so this is a very, very helpful way. The classification report is a very helpful way where developers can work on their solutions, and they can build better applications which are more representative of all the classes. Okay, so this is just to highlight to you a couple of examples of classification, and we'll talk about more use cases as we go forward. But I hope everyone's getting a sense of how we are actually building a full-fledged application. And now from here, we'll go to generation. Generation task is exactly the same. There is nothing different that we are discussing here. There are a couple of other parts that we will talk about, but the initial part of generation is exactly the same as what we covered before. So whatever we discussed in classification, generation is exactly the same. The only difference is you can just kind of ignore this part for a minute. I will talk about this part later on. The generation is exactly the same. You can see there's no difference, absolutely no difference. And here, when we cover generation task, we will take the example of a meeting summarizer use case. Okay, so what is the use case that we will take up right now? We will take the use case of a meeting summarizer kind of an application. This is what we will do for the generation task. Okay, so this is the plan ahead. So we'll start off with generation, discuss very briefly 5 minutes in terms of how the generation tasks workflow looks like. Very similar, few short examples, gold examples, uh, design the prompt, evaluate the prompt, but the metrics will be little different. Right, just like in classification, we talked about accuracy, F1 scores, confusion matrix. So here it won't be the same. Here it will be, the metrics will be slightly different. So we'll do that. I'll show you a case study. We'll solve a case study, and that's the general plan for the next 1 hour. So now we are looking at the workflow of a summarization or generation task. And when I discuss the generation task use case, We are seeing this in the context of a meeting summarization use case. That is the use case I'm taking up right now. Something very similar to what we saw yesterday. If you remember yesterday, we did a very similar kind of a meeting summarization task yesterday, where there was a transcript of a meeting, and based on the transcript of a meeting, you have to generate the summary of a meeting. That is what we are trying to do. Okay, so based on the meeting transcript text, you have to generate a meeting transcript summary. Summary of the meeting is what you have to create. And we want to generate an application for it. That's the idea. Yesterday, what we did, we just tried a random prompt. There was no evaluation we saw. We just wrote a system message and we gave a user input and we saw some response. But it was not a complete end-to-end workflow. What we are seeing here is the same application, but we are packaging this into a more end-to-end workflow where we take the data, we split the data into few short examples, gold examples. Using the few short examples, we design the entire prompt, and then using uh, the transcript in the gold examples, we generate the response summary, and then we test that response against the actual summary. Okay, so this is something very similar to what we discussed in classification, just that we're extending this to generation task. Okay, now everything is the same. The only thing that will change is the method of comparison. So if you remember in classification, we use something called accuracy. We looked at something called the confusion matrix. We looked at something called the classification report. So we evaluated the model performance using the confusion matrix and the classification report, because that is giving us the class level performance. So using the classification report, we can understand how is the model performing for each and every individual class. So class 0, how is the model performing? Class 1, how is the model performing? Class 2, how is the model performing? So we are able to understand the quality of the model for each and every individual task. And that's the way how we understood the idea of the uh, how to evaluate classification models. Now, when we talk about generation models, summarization models, generation tasks particularly, we cannot compare it like we did for classification. Why? Because the generated text, in this case, the generated summary, the predicted summary, will never match the actual summary. Please keep this at the back of your mind. So the predicted summary, whatever the summary the LLM is predicting based on the transcript, that will never match the actual summary. The predicted summary will never match the actual summary. Okay, so whatever summary the LLM is predicting will never match the actual summary. That's the way to look at it. And that is why we do not use accuracy as a metric. We do not inherently use accuracy as a metric. Because even if you use accuracy as a metric, what will happen? The accuracy will always come out to be equal to 0, or it will be very less. Classification was different. If you go back to classification, the last exercise we did, let's say the model predicted positive, actually also is positive. Like, you can't generate a different answer, right? In the system message, you are clearly saying that based on the sentiment, please output the response either as positive or negative. You are very clearly defining the bounds of the system. The response could not have been anything other than positive or negative. Even if you go back to the patent classification exercise we did, we were very clearly listing out that based on the patent text, we want the outputs to be only out of the 8 defined categories. We very clearly defined what those categories were. So whatever response the LLM will give will be only out of those 8 categories. That is why we call it classification, right? Let's say in your organization, you're trying to do some kind of document categorization. It will only be out of those 8 categories. The LLM will not generate something randomly on its own. But generation tasks are different. Generation tasks are where the output can be completely different. It's a much more open-ended problem, right? We were discussing this yesterday, right? We were saying, okay, typically for these kinds of things, the temperature setting should be much higher because the output can be something very different. Like even in this class, if I ask each one of you to generate a summary of the meeting, every single person will write the summary in a different way. Each person will write the summary in a different way. No two-person summary will be exactly the same. So that is why we do not use accuracy. We don't do a text by text, character by character comparison, but rather we will use a more of a semantic comparison. And here we will use something called a BERTScore. Now I will not be getting into the technical details of BERTScore. BERTScore is again a transformer based concept. So we use word embeddings and sentence embeddings to compare the the meaning, the inherent meaning behind what those summaries are relating to. But at a very high level, we are doing a semantic comparison. We are not doing an exact word by word or character by character comparison, but we are doing a semantic comparison. Semantic comparison basically means you are looking at what is the meaning of this summary. You're looking at the predicted summary. You're trying to focus on what is the meaning of this summary. What is the actual meaning that is present in this summary, and you're comparing that with the actual summary meaning. So this is the comparison that you're making using the BERTScore. Okay, so this is the only difference that we will see, and it is based on something called a word embedding. So anybody who is coming from again a traditional NLP kind of a background, and that's why I say there's a huge relationship of Gen AI with other preceding topics. Okay, if you don't know that, that's okay. At a high level, you can understand this some kind of a accuracy metric. But people coming from a traditional deep learning NLP background, if you have heard of word to vec, word embedding, glove, those kinds of models. Okay, skip gram architectures. If you know word embeddings, what they are. So this is exactly that. So you're taking the summary and you're somehow representing that summary in a sequence of in a vectorized form, and you're comparing that vector of numbers with the actual vector of numbers, right? So at a high level, I can explain the concept. Don't need to get too much into the detail of it. At a high level, I can explain the concept. Okay, so this is approach number one, where we use something called the BERTScore. And BERTScore is used in scenarios where you know the actual summary. The actual summaries are known to you. So this will work in a scenario where the gold examples are known to you. If you know the gold examples, this strategy will work very well. That is if the gold examples are known to you. But in a lot of real world scenario, if you think about it, in many real world scenario, the gold example will not be known to you, right? Classification tasks are a different ball game. You are trying to take something and you're trying to classify out of those 4 or 5 distinct categories. So classification tasks are different. Okay, so you have a series of 4 or 5 tasks, and you're trying to classify the text into one of those defined categories. That is what we are trying to do in classification. Okay, so there you can very clearly have a ground truth. We can have some explicit gold examples. We can have a ground truth or a test data. But in generation tasks, oftentimes in real scenarios, you will not have a ground truth data. You will not have a gold example, because think about it. If I give you a transcript of a meeting, what is the ground truth for what the summary should look like? Think about it. Do we even have a ground truth? Is there anything called a ground truth there? Is there anything called what is expected? No, right? It's very open-ended. Anybody can write a summary of a meeting, and all the summaries will be reasonably similar. But we don't really have a ground truth, right? We cannot really say that, hey, this is the benchmark summary. Okay, if I ask you to write a marketing advertisement, a generator, if you think of any kind of generation task, let's say generating a post, a social media post for some marketing campaign or for some new product launch that has happened. What is the ground truth for that? If I have 100 people in this audience write 100 different social media posts, all of them will be equally okay, right? It's very hard to write. And who will judge? Who will say this is right and this is not right? There is nothing called ground truth, right? It's very hard to define ground truths for generation tasks. Most of the time, you will not have a ground truth. But classification task is fixed, right? If I do sentiment analysis, if I give you a particular review, you will have a ground truth that, okay, this is positive, this is negative. There is no debate about that. If I say the food was bad, I hated the food in the restaurant, everybody will agree that that's a negative sentiment. There is no doubt on that. That is how I want my system to behave. So ground truth is defined. If you look at the patent or the document categorization use case that we talked about, given the text of the document, it is a ground truth. We all agree that that is a fixed constructions category. We all agree it's a physics category, because that is how I want my documents to get grouped in the future. So there is no doubt about that. Even if I have 100 people, 100 experts label that data, all 100 of those experts will say, yes, it is physics, yes, it is fixed construction. There is no debate about that. It's not an open-ended answer. It's a very close-ended answer. But in generation tasks, no two people will agree on the same summary, right? So how will you have a ground truth? Think about it. So if you have a ground truth, in rare cases, you will use a BERTScore. We use an embedding model to look at the meaning that is embedded in those sentences, and we compare them semantically. We do a kind of a semantic comparison. We don't compare them word by word, but we do a semantic comparison. We look at the meaning of summary one, predicted summary. We look at the meaning of the actual summary, and that is how the comparison is done. It is usually on a scale of 0 to 1. We will see the demo shortly. It is usually on a scale of 0 to 1. The higher the score, the better the model. And all it does at a very high level, all it does behind the scenes is, if I have to kind of compress this discussion at a very high level, all it does is it simply represents this as a vector of numbers. So you have something called a predicted summary. We represent the predicted summary as a vector of two numbers. Let's say 0.1, 0.23. That's your predicted summary. And this is the actual summary. And you represent the actual summary as a vector of two numbers, which is, let's say, 0.11, 0.22. See what we do. So the embedding model, what it does is it takes a text summary. Let's say the summary is like, okay, it's a big 100-word summary. So in a way, intuitively, what it does is it takes that text and it converts that to a vector, a numeric representation. And the actual summary also, it converts it to a numeric representation. And then what we do is we do a comparison. We use different types of distance formulas to compare. You can look at something like a Euclidean distance. You can look at something like a cosine distance. Okay, so you can compare 0.1, 0.23 with 0.11, 0.22. I think they're very close. They're very similar. So then you can say, yes, the BERT score is very high because these two documents are very similar. So we can confidently say the predicted summary is very similar to the actual summary, the ground truth summary. So the LLM model is working as expected. Okay, so this is a very high level idea as to how we use BERTScore. Now, if we don't have the ground truth summary, what happens then? Then we use something called LLM as a judge. This is approach number 2. So let me quickly go and remove this part. So if we do not have the predicted summary, what we do there, this part will go away now. This is oftentimes going to be the case. You will not have a ground truth summary. If this is not there, then what do we do? The same approach. You define a system message, you take the few short exemplars, right? Again, this is optional. Sometimes even the few short examples are not given. That is also optional, by the way. Whatever, you design the prompt, and once you have the gold example, you take each and every text from the gold examples section. In this case, the transcripts you take, the X you take, and based on that, you pass it to the language model to get a summary or the transcript of the summary of the meeting. And then you don't have a actual to compare. So you give it to one more LLM, and this is what we use as LLM as a judge. Okay, very popular way of evaluating language models. So we use another language model at the very end to evaluate the performance of the first language model. The first language model is the one that is responsible for generating the summary or doing the generation task, whatever. It could be a summary, it could be creating a post, creating an email, creating an article, whatever. The first LLM is responsible for performing the generation task. In this case, create the meeting summary. Based on the gold example, what is the predicted summary? Generate that piece. And then you take those generated summaries and you feed it to another large language model. This is usually a more powerful model. You can take a higher variant model in this case. You feed it to one more language model, and that language model acts as a judge. And you can design that language model again the same way. You can say, okay, there will be a system message, there will be a user message, right? You can design the language model the same way, and you can ask that judge model to rate the performance. How did the original LLM perform? You can ask the judge model to rate how the original LLM performed. Okay, so this is the way how you evaluate language models, especially for generation task in cases where the actuals are not known. Okay, so this is the workflow. The code is very simple. Now we'll see a small code implementation, how it is really done. Okay, so we'll see this in action now. All right. So I've already uploaded a folder called generation tasks here. And what I'll do is I'll take you through the first demo of how the generation task is done. Okay. And it'll be following the exact same workflow that we covered here. Let us see. Let us see a very simple example of how a generation task is performed. And I will run the code also for you in the background. Very similar. You don't have to do it. So first thing you will have to install the BERTScore because BERTScore is a different package. It's a different library that needs to be installed. So if you're running the code, you need to install the BERTScore. And these are some evaluation metrics that you need to install also. And then you will go and do the same stuff. This is the same stuff. Remember, this is the different Jupyter notebook, but your API keys, what you did yesterday, is already saved. So nothing to change here. So I will just read the API key, get the API key from my secrets, which is the environment variable in Colab. So save it in this variable. My endpoint URL is the same. The version is the same. The deployment name is the same. Nothing to change, but you need to change it as per your deployment names and all that. Okay. Just make sure you do that. And now let us come to the actual problem. Okay. So this is the judge use case, by the way. This is what we will demonstrate here. So remember, the first LLM is responsible for creating the summary. This is exactly what we will see. So we also have a very similar summarization use case here. So we take the input text and the first language model will generate the summary. And the second language model, the judge model, will take that predicted summary and it will give a quality score. So to the second judge model, what do you give? You give the original input text, you give the predicted summary, and you ask it to rate it. You ask it to rate it, okay, based on this input text, whatever summary was generated, how did it perform? So one very important thing is don't use the same model. If LLM1 and LLM2 should be different, LLM2 should be a different model. If you use the same model, then obviously the score will always be high. But you use a different model, it's like a judge, it's like another person. So you go to another person, a judge, and say that, hey, this was the text and this is what the first model predicted. So tell me how good the prediction was based on this text. Okay, so that's the way to look at it. All right. So now moving on, let us just see the use case. So we can, again, the same idea. The idea is the same. We are just assembling the data. So this is what we have. We've got lots of dialogues and summaries right now. So we've got lots and lots of example dialogues. I think the initial uh, installation is still happening. You can see. Yeah, this takes a little time actually. So you can see it's a big install that's happening. So okay, now it's successful. All right, good. Evaluate will be faster. Okay, okay, perfect. And now we will load the data. This should be fairly fast. Okay, and you can see this is my example data. We have the dialogue and the summary. So we have the dialogue and the summary. The dialogue summary, dialogue summary, dialogue summary. So this is my data. So as I said here, the actual summaries are given, but in a lot of real world applications, the actual summaries may not be given. That may not be always the case. So here the actuals are given to us. Okay. So rest of the part is very similar. You can see the system message, very basic system message, summarize the dialogue mentioned in the user input. Be specific and concise in your summary. You can make it more detailed if you want. You can add some more details, what kind of things you want to be in the summary. You can make it more detailed if you want. And this is a few shot prompt. So we are taking again a sample of uh, this will be a bigger, a slightly bigger, few shot prompt because the summaries are actually quite big. The initial content is quite big, and so that's why it's a little bigger. You can see. So yeah, so this is the 4 few shot examples we have: user, assistant, user, assistant, user, assistant, user, assistant. So these are the 4 few shot examples we have right now. Okay, and now you can you can evaluate the model. I'm not doing that because this might take a little time. So I'm not doing that, but so now what will happen is you will go and evaluate the model, and after you evaluate the model, it will go and you can compare calculate a BERTScore. And if you see, this is the BERTScore that we are actually computing. So we are getting a BERTScore which is close to 90.66. Remember, here we already have the ground truth data. So because we have the ground truth data, we are generating the predictions and we are comparing with the ground truth. You don't have to do it manually. You don't have to do the BERTScore computation manually. All that we do is we just go ahead and use the BERTScore library. Okay, so we say BERTScore compute, we give the predictions, we give the references, which is the actuals, and the BERTScore will give me a number. And turns out here 90.9 is a very high value. So the BERTScore ranges from 0 to 1. Okay, 0 is very bad, 1 is very good. So if the value is close to 1, 0.9 is very close to 1, right? So if the value is very close to 1, that means the predicted summaries are very close to the actual summaries. Okay, the predicted summaries are very close to the actual summaries, and this is expected because if you think about it, the GPT-4 Omni, the GPT-4o model that we are using is a very powerful pre-trained model, and the zero-shot learning works very well. This is not a domain-specific thing; it's a very general summary that we are trying to create. And these kinds of language models are inherently very good in summarization. It is not something where I have to teach it or something. It's already very good at these tasks. So that's the reason why even in a very basic kind of prompt that we wrote, we're getting a very high accuracy overall. But in cases where the original actual results are not known, we will use LLM as a judge. So same thing, we get the predictions, remember, and now what we do is we define the rater model. Now it is just for the demo that I've taken the same model. Okay, because otherwise I have to create a separate deployment. So what you need to do ideally is you need to go and create a separate deployment. So go here, go to deployments, and you need to actually create a separate deployment. Okay, just like we have used GPT-4o, you need to create a separate deployment, and then you need to say the rater model is equal to that model. You'll say model name equal to whatever. Let's say this is GPT 4.1, you say, and then you say the rater model equal to GPT 4.1. So that's the ideal way to do it. But anyways, so you can define the rater model, and the rater model is a separate LLM. It will have its own system message, and see how we are defining the system message. Very detailed, right? We're explicitly stating that the judge will have to give a score of 1 to 5. Okay, you look at the task at hand and evaluate on a scale on a scale of 1 to 5, 1, 2, 3, 4, 5. 1 means very bad, 2, 5 means very good. So the metric is not followed at all, and 5 means the metric is followed completely. And what is the metric we are discussing? The metric is this. The summary should cover all aspects that are majorly being discussed in the dialogue. Now, it's a very basic metric I've given, but you can make it longer, you can make it bigger. It is just how you teach a judge. Imagine that, like a judge is coming for some kind of an audition or some kind of an evaluation, some contest is happening. So even the judges will have to be briefed, right? So you are the person who is briefing the judge. Judge is already a very powerful model, but the judge has to be briefed. What do I have to do, right? So the metric is where the judge is being briefed. Okay, this is what you need to do. And this is where the judge is getting a kind of a criteria what to follow. This is like a rubric. Like in exams, when you write, you have a very proper evaluation rubric. What is graded, how it is graded, 2 marks, how the 2 marks is assigned, like that. Okay, so this is like the complete rubric that is given to the judge. Okay, so now the system message is defined. What is the user message template for the judge? So what are the things the judge needs to evaluate, right? It needs the dialogue and the summary. This is the thing. So the dialogue is the original dialogue from the gold example, and the summary is the predicted summary. Whatever the previous LLM is predicting, that is what you need. Okay, so we have the whole thing, and now you can kind of check. So based on the dialogue, this is what the first language model predicted, and based on the prediction, this is what the judge model basically evaluated. And you can see right at the end, I can just show you one of those examples, rating 0. Ratings is the data frame, right? I'm saving this in the ratings data frame. And if you see rating 0, you can see that in this data frame, if I see, this is what the judges rated. Okay, the summary is followed mostly, so the rating is 4-star. You can see this is how it's appearing. So the entire judges evaluation is coming up right now. But oftentimes, we don't need so much of evaluation. I mean, so much explanation we don't need, right? Explanation is needed only when something goes wrong. When something doesn't go wrong, explanation is not needed. So what you want to do in that case is you want to go and maybe refine the system message further. You can say, okay, do not explain the reasoning behind the answer. Don't explain the reasoning behind the answer. Just output a numerical rating 1, 2, 3, 4, 5. Because you have to understand that ultimately we are probably trying to use these language models output and saving it in some other structured relational databases, just like what we did yesterday, information extraction. So maybe the judge model, the output of this model is used downstream in some other system. That's also very common, right? The output of the model is probably used downstream in some other system. In those kinds of cases, you want to get a numeric output rating, and you want to use that output downstream in some other system. That's the way to look at it overall. Okay, so that's the rater user message. Again, you can see, and you can see here the ratings are coming as a number. Not all the things are properly followed. So we need to further fine tune the system message, but mostly this is how we want it. We want to see, like, this is a way that will help me evaluate, right? If I want to do a continuous a production grade evaluation, what will happen? I can do a week on week, a day on, a daily evaluation. I can do a monthly evaluation, fortnightly evaluation, that how my language models are working in production. Okay, so this is not only during development time, this is the same way that you will evaluate your language models while they are running on production. So while my language models are working in production, while they're generating the outputs, you can evaluate those language models in production, how they are performing. So every 100 queries, you can sample 5% of the user queries. And for those 5% of queries, you can pass it through a judge model and let the judge evaluate how that model actually performed in production. And that is how we can get some kind of a performance report, some kind of performance metrics we will get in terms of how the LLMs are doing. Okay, if there is any decay in quality, then we can decide whether to fine tune them and things like that. Okay, so we can get a week on week performance report. Okay, week one performance was up this much percent, week two the performance dropped 10%, week three it further dropped 20%, and then we can start questioning, okay, why is the performance dropping? Because the judge is rating it low. Every week we're seeing, okay, the ratings are going from 5 to 4 to 3 to 2, and that's a concern. So that's why the production evaluation part is also a very, very central role that these kinds of LLMs as judges will play. Okay. All right. So I hope everyone's getting a very good understanding of the workflow, how generation tasks are actually done. And now we will do a very similar exercise. Now we will do a very similar exercise on generation tasks, just like how we did for classification. All right. So now I will quickly take you through the solution for the autoresponder use case that we discussed. I'm not running it because it will take time, but this is again the data set that we have. If you see, so we have inputs, which is the mail or the particular question that was asked, and we have the response. So we have the few short examples that are given, and this is what I was actually discussing. If you do a value counts, you will realize that there are only five unique complaint response categories that we have. And another very, very important thing I wanted to highlight is the distribution of the data. You can clearly see that there is a huge amount of imbalance in the data. So there are 18 different examples of the first type of response, but there is only one example of the fifth kind of response. So we have a huge imbalance in the data that we can see right now overall. So the data is very, very distributed in a very, very imbalanced manner. The same for the gold examples. And this is the other aspect that we were discussing. So you can see there are five unique examples in five unique categories in the few shot examples part, whereas there are six unique categories in the gold examples part. And even that also goes to show that the distribution of my data is not ideal. So ideally, we should have the same type of examples and the same number of examples in both few shot and gold. Okay, so the distribution has to be the same. So obviously, the gold example should have more number of examples because, as I told you, 20% for few shot, 80% for gold. That's going to be the ratio usually, but the distribution has to be similar. Here, the distribution itself is very, very different. So now we try out the prompt engineering part. You can see that we are saying, respond with this thing. This is the detailed system message, and we are trying out with different variations of the system message. This is a few short part. This part is straightforward, very similar to what we talked about. And see, I'm solving it like a classification problem. The moment I solve it like a classification problem, I'm getting only a 6.25% accuracy. This is not surprising because I told you that the data is very, very imbalanced and it's not right. We need to do it in a very detailed way. So the moment I solve it like a classification problem, we're getting a very, very poor result. And why is it classification again? So although it sounds like a generation problem, that we want to generate or predict a new response, but it's not an open-ended response. If you look at company policy, the response only has to be from these five distinct categories. The response only has to be from these six distinct categories. So it's not exactly an open-ended generation. If I ask 20 of you in the class to, uh, you know, give a company response to a particular input, you will not give random responses. You will want to give a response which is in line with the company policy. And that is why, although this looks like a generation problem, it is actually a classification problem. So the way we should ideally do it is we should go and label encode these responses. This is response 0, response 1, response 2, response 3, response 4, and response 5. The sixth response will be actually response 5. Again, the distribution is not right, I told you. And then we will use a prompt to a system message will clearly specify that output these 5 to 6 different types of responses and then go back and do the prediction. So that's the way how it will work out. And this is actually the other problem that you're seeing. Okay, if you take a look at it in the system message very clearly, I only give 5 categories. Can you see? This is again the distribution of my data is to blame. The data curation is to blame. So I've only given the 5 categories. And as I told you, this is not a good practice to give the whole text. Give the labels 0, 1, 2, 3, 4. Okay. So only 5 categories are given. But remember, in the gold example, the validation, the test set, we actually have 6 categories. That's the problem. So although I'm giving 5 categories here, but in the validation set, I've actually got 6 categories. And that is what is really causing the problem. And you can actually check which one is the one that is not present. Okay, anybody can find out which one is the one not present. So company chooses not to, this is there. Believes it acted, this is also there. The third one is also there. The fourth one is not there. This one is not there. The company believes complaint caused principally by actions of third party outside the control or direction of the company. This one is not there. So this is there in the validation set, the gold examples, but this is not there in the few shot examples. So there's no way to uh, explicitly. So in a way, my LLM will not even generate that kind of an output, and that's a problem. You can see how serious this flaw is. This is actually an expected response, but because I don't have it in the few shot, I'm not putting this in the system message by mistake. So we have to tune the system message, and because of these kinds of reasons, my overall classification accuracy is very very bad. But as I told you, we can modify the few shot prompt. Here I'm modifying it. I'm making it better. We have introduced some chain of thought prompting, COT prompting. And once I do that, I'm getting a 31.25% accuracy, which is much higher. And if you come all the way down, this time I'm trying using BERTScore. This is what most of you did. You tried with BERTScore, and with BERTScore, we are getting a very high answer. And what is the reason why we are getting a very high accuracy, a very high BERTScore in this particular problem? Because semantically, the responses mean the same. The meaning of the responses are the same, although there are 5 to 6 different categories. But if you look at them semantically, they're all talking something to do with company responses, either company responding or choosing not to respond, or withholding the response, whatever. But they broadly all mean the same thing. Okay, so in terms of classification, if you just look at the accuracy, it will be very bad because we want the exact response to come. But if you look at a semantic comparison, are they similar? Yes, they are very similar. That's why the BERT score is high. But as I said, the BERT score is not the best way to evaluate these kinds of things because it's company policy. Even if one or two wordings are changing, then maybe some customer, if you're giving a wrong response, even if one or two words in the customer response is wrong, in lawsuits and in a legal, in the court of law, it can be very expensive for the company. Okay, so these are very real things that you need to consider when you're building problems, when you're solving problems. There is one more very interesting use case I wanted to generally talk about. This is already uploaded in your folder. You can take a look at the generation folder. I've already uploaded that. This is actually how we use generative AI for content summarization. Okay, how do we use generative AI for content summarization? So to explain this in a little bit more detail, let me go and take up an example. Okay. So what I have done is I've actually opened up a YouTube video just to show you the real use case, what we are trying to achieve here. So you can see, very interesting. So all these YouTube videos, what they do is they come with subtitles, right? All of you know that. I'll turn on the subtitles and captions basically. And this is a video where they explain language models. So very interesting. So the language model is explained here in this particular video. All of you can see. Okay, just 1 minute, please. Okay. So the objective of this exercise would be to look at the video. So to go to a website, download the YouTube video, right? So to go to the website, we want to download the YouTube video, and from that YouTube video, extract the audio component out of it. That can be done. There are Python libraries which you can use to do that. I'll show you very, very shortly what those libraries are. So we can go to any YouTube video. We can download the YouTube video. We can extract the audio component out of it. Only the audio component we can download. And there are a lot of tools you can use for that. A lot of these video editing tools, they come with ready-made softwares which you can use to, detach the audio. Only the audio part can be detached. And in Python, you can very easily do it. And from that audio, we will use speech to text, right? Although here, by default, YouTube is giving you the captions, but behind the scenes, remember, behind the scenes, it is using a deep learning model to create the captions. Okay, so some kind of deep learning model has been used to generate the captions. So that is what is happening behind the scenes. Real time, the caption generation is happening. So based on the video, the model is real time generating the captions. It is using a speech to text model. And if you remember from yesterday's conversation, we were discussing that beautiful use case of Lura AI. Remember, Lura AI is a model that is used to uh, it helps you basically learn English, right? You say something in English, and Lura AI gives you feedback in English. So when you say something, you're doing speech to text. Internally, it is getting converted to text. So I will, let's say, it asks you to pronounce, let's say, my name is Sayan. So I say, my name is Sayan. So what it does, it actually takes whatever speech I'm using, whatever audio pattern I'm using, it will convert that speech to text using a Whisper model. Okay, so Whisper is a model that is given by OpenAI. OpenAI has a model called Whisper, which is used for doing this exact same thing, speech to text. The first level will be speech to text. Whatever I'm saying will be converted to text. That text will be processed by your language model behind the scenes, and then the summary will be returned back. That is exactly the use case of this thing. Okay, so you take a YouTube video, take the audio part out of it, speech to text, take the text part of the audio. So do the entire transcription of the YouTube video, take the complete text, whatever is talked about in this hour-long video. Okay, and then what do? We take that whole text and generate the summary. So it's a video summarization use case. In short, in 5 words is video, 2 words is video summarization. That's what we are trying to do. Okay, and this could be very helpful, right? Because the creators can now use this kind of technology, and when they want to create some video, like in this case, Andre Katpati, he's a very popular editor. Okay, it's a very good author, actually. He has some very good videos, right? So what they can now do is they can now look at the summary, they can look at the captions, and they can themselves internally use a transcription model. Then they can use the LLM to summarize it, and they can get this thing. YouTube does it automatically for you. If you're a YouTube creator, YouTube gives you tools which can automatically do all this for you. But now we understand how this thing happens behind the scenes, right? Even if you look at Truecaller, Truecaller has some of you might be using Truecaller. So Truecaller has come up with a lot of incredible features. Okay, and one of that is obviously call summarization and call transcription. This is not a new thing. A lot of companies are coming up with these kinds of solutions today. So Truecaller has this thing called call recording and call transcription. So what you can do is you can record the call. Okay, you can record the call, and you can also go back and generate an entire summary of the call. Okay, so all those kinds of things are there. If you have a Galaxy device, Galaxy AI also comes with these kinds of features. Samsung Galaxy. So next time somebody calls you, you can record the call. The whole transcript of the call will be recorded. It's a huge amount of text will be there, and then on the basis of that, the summary can be generated. And you will get a, just like a meeting summary, you will get a call summary which talks about what kind of things were discussed and all that. And you'll be surprised to know that it is very much language. It takes into account the language. So and that is the next big revolution that is happening today, where all these language models are working with respect to different languages. Like you might know the Grok the 3 model by XAI. XAI is the Elon Musk's company. The Grok 3 model actually does very well in Hindi. Even if you say something in Hindi or write something in Hindi, the Grok 3 model actually does pretty well in Hindi. Even ChatGPT for that matter, and it depends a lot on the models. But if you look at DeepSeek, DeepSeek may not do that well. Okay, so DeepSeek may not do that well. But if you see many of the other models, like if I go to ChatGPT and say, kaise ho, if I go and ask this kind of a question to ChatGPT, if you see, look at this, it will actually answer it. And what is the reason? Why is it working? Because it has been trained based on these kinds of tokens. And not only that, it is actually, what do you say? It's using Hindi English as they call it, no? Like normally when we use the English keyboards, we also write it this way, no? We don't use the Hindi tokens. But this is interesting. This is actually very hard, Actually very hard for the model to understand. It's all about associations. The language models are all working based on associations, how certain types of words are getting used. So if you look at the word may, if you look at the word thick, main means something very different in English, right? Main is what? Main means something important, main. So main, the word means something very different in English. But the word main, the token main, in the context of what you are seeing right now means something very different. So all these language models are working based on context, association. What is this on the in the context of all this, right? And you can try it out. You can now go to maybe let's see if I can, if I can do this. Mm. See, I'm just randomly pinging some tokens. You can just actually kind of see whether it works or not, and you will see that it actually does work. You know, so Chat GPT as we speak today is trained based on Hindi tokens. So you can actually interact with Chat GPT even in Hindi. It doesn't have to be only the Hindi English kind of tokens. So Chat GPT has also been trained based on this. This is again a feature of the language models. Internally, the models that are there, what they are trained on. But this may not be the case for DeepSeek. ChatGPT may not be that good in Chinese, but DeepSeek will be very good in Chinese because it's a Chinese model. It has been trained on more Chinese tokens, and so you need to be also aware of these kinds of things. All right. So now we will be entering into the next phase of our discussion, which is retrieval augmented generation. It's a beautiful topic. So far, over the course of the last day and the last few sessions, we saw how to write a prompt. We saw how to build basic LLM applications in the context of classification and generation tasks. We actually saw some basic applications, not just writing a prompt, but we saw how to set up evaluation, how to split the data into gold examples. And I think this gives you a little bit more clarity in terms of use cases at this point in time. Now, after we complete RAGs, you will get a much better understanding of organization specific use cases. So this is a very, very important topic because especially in organizations and enterprises, RAGs are a absolute gold standard today. Everyone is looking to do RAGs because one of the reasons is because it helps you take into account internal company data. Internal company data. So you might have some kind of a document. You might have some kind of a document. You might have some kind of a PDF file, and you don't want to upload that PDF file anywhere. It's a very confidential PDF file that you want to keep in your company premises, in your server. At the same time, you want to use the Chat GPT model. So it's a very difficult thing, right? Because all this while we are saying that you have to send your data to GPT. Okay, so to use all these LLMs, to use all these large language models, you have to use the API, and there you need to send the data. Because that's what we are doing in the prompt, right? We are defining a very detailed system message. We are having a very detailed user message, and we have to send the whole data for the LLM to give a response. But what if I want to work with my own company data? What if I have a huge file? What do I do with that? What's the way to work with that? I am not comfortable in sharing that file with ChatGPT because the only option is to send it to ChatGPT, upload it, and send that whole document as part of a prompt. Not that you cannot do it. You can give that whole document as part of a user input. You can do that. You can copy the whole text and you can do that. But then that is confidential data. You cannot afford to do that. So what is the alternative? That is exactly where RAGs come in. So RAGs, this is the broad workflow that we will discuss. We'll see the business use case. We'll take another 2-3 minutes to talk more about RAGs. How are they beneficial? We'll look at the workflow. We'll talk about vector DB and we'll see hands-on implementations. I'll show you one end-to-end demo, and after that we will do one end-to-end case study, which each one of you in the audience will be doing. So that's the plan. And this is just to give you a very pictorial understanding in terms of what we are doing in a RAG system. So we have a document store. This is the internal company proprietary document store that the company is maintaining. And this is where the company's confidential data is present. This is what I was talking about. Okay. So this is where the company's confidential data is present, and you don't want to expose it. This is very confidential, right? This is let's say some bunch of last year sales data or revenue guidance. You have revenue guidance for the last years or employee salary data, which is confidential. You don't want to release it to anybody. Okay, so this is part of your document store. You'll be having it in part of, in your file system. At the same time, you still want to build a chatbot on top of it, where people can ask questions and get answers. The same way that we can do in normal GPT models today. You can upload a Word document and you can ask questions and you can get answers to questions. That's the way how this particular process will work out. Okay, so everybody can understand. I hope this is the idea is absolutely clear what we are trying to achieve. Okay, now let us look at the workflow. This is the workflow of a RAG system. Now there's a lot going on. So what I'll do is I'll explain step by step in terms of how a RAG system is designed. So RAGs are a slightly long topic. So we'll do it in two phases. First, today we will see basic RAGs. Fundamental RAGs is what we will discuss in today's session. So we'll talk about building a RAG, using a vector DB, how to create embeddings. This is basic RAG. And some part of tomorrow we will spend on advanced RAG, advanced retrieval. So how do we make it more efficient? How is it done in the real world? Right? Some more advanced topics in RAGs we'll try to also incorporate. Okay. Now, at a very high level, okay, all of you just give it a glance first. Maybe you can all take 30 seconds to just give it a glance what's going on, and then I'll explain. So the first part, what we have is, and what I'll do is in this demo, I'll try to take an example of some PDF files only. So let me take that same example and explain this to all of you. Okay. So let's say we have 100-page PDF file, right? So we have a PDF file. Okay, sorry, I think the annotation should be enabled. Just a minute, please. So we have a PDF file, which is 100 pages. And this is, let's say, containing company policy. As an example, this is the company policy PDF file. Okay, so the use case is more like, you can think of a use case where an enterprise wants to build a HR chatbot, some kind of a human resources chatbot where, some kind of a human resources kind of chatbot we want to build where, let's say, you want to know how many leaves are offered in a year. So yes, there is a very detailed company documentation that is also present. You can, of course, go and consult the documentation. But how do we get that answer a lot in an easy way? Okay, so the company wants to create a chatbot, employee HR chatbot, where basic human resources questions could be answered by the chatbot by taking the data from the company policy. Now, company policies are very confidential. You don't want to release it online. You want to, you don't want other people to know, other competitors to know. There might be some very specific compensation packages which are very specific to your enterprise. You don't want to release it. So it's very confidential data. So you want to keep it in-house. You want to keep it in-house in your document store. At the same time, the chatbot should be able to, answer questions based on this. Let's say one fine day you reach out and ask, okay, how many leaves are there in the year? So the chatbot will be able to look up all this information and say, okay, there are 20 leaves in a year, something like that. Okay. Okay. What is the hike policy? Okay. What is the progression policy in the enterprise? Okay. What are the maximum raises given? Or how do I shift to a different domain? Which is again a very common question people have. So let's say you're learning GenAI. So how do I shift? How do I progress to this? So these are again HR questions. So they might be the model will be able to look up the information and give responses. Okay, that's the idea. So how it works out? Let's see. So we have a PDF file, 100 pages. So first thing that you need to do is you can't, so this is too much to process, right? I know 100 is a very small number, but this could be huge. In fact, some of the exercises we will do in the session, we will actually take very big PDF files. They will be very big. Each of them will be very, very big PDF files we will take. So it might be too much to process all those files in one go. Okay, so processing all the files in one go might be very difficult. So what we will do instead is we will go and break it into chunks. We will break it into pieces. Okay, so and uh, it could be something very simple. Like let's say we can say each chunk is one page. Each chunk is one page. So we have chunk one, chunk two, chunk three, all the way up to chunk 100. I want to clarify it doesn't necessarily have to be like this. Now, chunking, there are different strategies of chunking. Chunking can happen in different ways. There are semantic chunkers that can be used to chunk based on the meaning of the context of the document, right? Uh, we can also use the fixed size chunking, like we can chunk based on pages, we can chunk based on certain number of characters. Every 300 characters, I want to create a chunk. Every 500 words, I want to create a chunk. So there can be different ways of doing chunking. But broadly speaking, we take the entire 100-page PDF file and we try to divide that PDF file into 100 chunks. Simple. Every chunk is one page. Simple. Now it's more manageable. Now what we do, because see, this is all text data, right? Even when you chunk it, even those 100 chunks that you see, this is all text, right? This is everything is text data. Each of those 100 chunks are basically text. Chunk one is the whole text present in page one. Chunk two is the whole text present in page two. Chunk three is the whole text present in page three. Chunk four is the whole text present in page four, right? So every, okay, just 1 minute, please. So every chunk is ultimately text. Now what you need to do, the next step, what you need to do is you need to go and save these chunks in the vector DB in an embedding form. Remember I told you that machines cannot understand numbers, right? Sorry, machines cannot understand strings. Okay, so convert text to numbers. Text to numeric embeddings. So how do we convert the text to numeric embeddings? This is done using a vector DB. This is the same idea that was playing out during the BERTScore. If you remember, I told you very briefly that how you take the sentences or the generated text and how the machine is converting that into the context, into the embeddings, right? So the idea is very similar because machines cannot understand text. Machines cannot understand strings. So you take each and every one of those chunks, which are nothing but text, chunk one, chunk two, all the way up to chunk 100, and you somehow represent them as a vector of numbers or features as we call it. I'll give some random numbers, F1, F2. So we are representing every chunk as a vector of two numbers. Let's say chunk 1 is 0.1, 0.2. Chunk 2 is 0.11, 0.22. And chunk 100 is 0.9, 0.8. Okay, so I'm just saying that the embedding size, okay, just a minute. I'm just saying the embedding size is equal to 2. What does it mean? It means that I'm converting every chunk into a vector of two numbers. I'm vectorizing the text. I'm basically representing the chunks or basically text here as a vector of two numbers. Now, why two? No particular reason. It's just an example that I'm showing you to explain the concept. But you can decide how many and what kind of an embedding model that you want to use. And there are separate embedding models that will do this for you, right? So this is not a manual process. So after that, so chunking will be done by chunkers. There are a lot of these chunkers that are available that you can use, which we'll see in the demo. And even the embedding the part where we are doing the embedding, even this embedding will be done using, just 1 minute. What happened here? It got removed by mistake. Okay, yeah. So even the embeddings will be done using embedding models. And different embedding models will embed in different ways. Some embedding models are very advanced. They might take each and every chunk and create 1,000 dimensions, or they will take the text and convert into 1,000 numbers. And remember, the more the embedding size, the richer the context. The more powerful models will take the text and generate more numbers out of it. It is trying to represent the text in terms of numbers. And the more the number of numbers, the richer the representation. You're able to represent the text in a richer manner. That's the context. Anyways, the vector DB creation is done. The vector DB works like any other relational database or NoSQL database. Think of it that way. The ideas are very similar to a NoSQL DB. So you just store unstructured data, and it's not only with respect to text, it's also with respect to pictures. Although we are not discussing images right now, but the idea is very similar for images also. In case you have a question, how do we save pictures? The idea is very similar. Just like here, we take the chunks and we store the chunks and we represent the chunks as numbers. The same applies for pictures. We store the excuse me, we store the images. So image 1, image 2, image 3, and then we represent those images as numbers, as a vector of numbers. The idea remains very similar, even with respect to pictures. Now, once this is done, once we have created the vector DB, now we know we have the chunks and we also have the representations for the chunks. Now come to the second part. This is usually the first part of the whole RAG workflow, the vector DB creation. Even when we see the demo, we will see the exact way. The first part that we will do is the vector DB creation. We take the document, and from the document, we do the chunking and we create the vector DB. And this process usually takes time. This process is usually very compute intensive. And sometimes GPUs are needed. We will need to use graphical processing units, GPUs, TPUs, advanced hardware. More compute is needed to perform this part. Okay, just keep this at the back of your mind, because this is a one-time process. This is not something that you have to do every time. So right at the start of your project, the vector DB creation is a one-time process. You take the entire company's data and you create the vector DB once. And then obviously incrementally, as changes happen, you can update, just like how you do in a database. If you have some new records that are coming or some new pages are getting added, you can update in the vector DB. But the initial creation part will take time. Now let's talk about the retrieval. How does the retrieval happen? Let's talk about that. I will use a different color just to highlight it. So here you ask the question. Now here you ask the question, how many leaves we get in a year? How many leaves we get in a year? Remember, that's the user query. This is the user input. So this will be some kind of an application that you will build, right? So the users will have no idea about all this RAG and all that, right? So you're an employee in the company, and you will use some kind of a application, or you might have a mobile device where you can access it. You will have some kind of a user interface where you will go and type this question, and that's your user input. That's your user message query. Remember, machines cannot process text. Machines don't understand strings. So again, that query has to be converted to numbers. So machines cannot process text. Machines don't understand text. So what has to happen? That query has to be converted to a numeric vectorized form. So this entire query has to be converted to a numeric vectorized form. So whatever query we have right now, let's say the corresponding embedding for that query will be 0.12 and 0.23. I'm just giving a ballpark number, okay? Let's say this is the corresponding vector embedding for that query, 0.12 and 0.23. So whatever query the user is asking, the user message will also need to be converted back to its corresponding embedding. And now we will have to check, the retriever module will go and check in the vector DB that this question is similar to which of the chunks. So whatever question we are asking here, this question is similar to which of the chunks. which of the chunks that this question correspond to. And that is how the retrieval will happen. So based on the question that the user is asking, based on the I think this is understandable. So I think the orientation changed a little. So that's okay. It's not a showstopper. People can all make it out what was written. So anyways, so just to clarify, we took the documents, we chunked it, we created the chunks, and then we saved it in the vector DB. And in the vector DB, as I was mentioning, the chunks are all saved in an embedding format, right? So every chunk is converted to a vector of numbers, and those embeddings are what are saved in the vector DB. Now, when the user is asking a question, so here the question that is asked by the user is, hey, how many leaves do we get in a year? This is what is written here. How many leaves do we get in a year? Now, this text, machines cannot understand the text, right? So this text has to be also converted to its embedding. So we have to convert this text into its respective embedding. We will convert this text to its respective embedding, and let's say the embedding looks somewhat like this: 0.11, 0.23. So this is the corresponding embedding that we are getting, 0.11, 0.23. And now the retriever will go and go back to the vector DB. The retriever will go to the vector DB and check that whatever user question is asked, that user question is similar to which of the chunks in the vector DB. So whatever user question is asked, this user question is similar to which of the chunks in the vector DB. That's the way to look at it. So whatever user question we are asking, which of the chunks is it the most similar to? So this user question is most similar to, let's say, the first two chunks. This is the distance formula that we are checking. I think you can relate to it. Like you can see 1.12, 0.23. This set of numbers is very similar to 0.1, 0.2, right? So this set of numbers is very similar to 0.11, 0.22. So it's basically looking at those 100 chunks. We are looking at the 100 chunks and retrieve the top two chunks based on similarity. Now again, it doesn't have to be exactly this way. It doesn't have to be exactly the top two chunks. And again, we can decide that it's a hyperparameter. We can decide how many chunks we want to retrieve. So here is an example. So given any user query, I want the retriever to retrieve the top two chunks. Whichever chunks are the most similar, the top two chunks I want to retrieve. So here chunk 1 and chunk 2 will be retrieved. You can see C1 and C2 will be retrieved. And this will be now part of my context. Okay, this will be part of my context. So until here, I hope it's clear. So until here, everything was happening on premises. Nothing leaves my server, nothing leaves my enterprise. Everything is happening in my local computing infrastructure. The documents are maintained locally. The vector DB is hosted in my local server. Although there are cloud vector DBs you also have, but if it's very sensitive data, you can host it locally. Okay, so vector DBs are all hosted locally in my local infrastructure. Okay, even the retrieval will happen locally. So based on the user query, you will retrieve the top chunks. Even that retrieval will happen locally. And now you have those chunks with you. This is the last part where you're invoking the GPT model. So in the LLM, what you're sending is just these chunks. You don't have to send the whole data. You are only sending the chunks. Okay, so what will happen at the final step? So based on this question, the model has retrieved the top two similar chunks, which potentially answer the question. But then these chunks are in a very haphazard manner, right? I told you the chunks are basically nothing but page numbers. So because the chunks are page numbers is kind of very haphazard right now. So now what you want to do, you want to go and effectively use a large language model to streamline the response. So now the chunks are nothing but disorganized pieces of text that are retrieved. So now you will go and send this data to the large language model, and the large language model will give you the refined summarized response. And what are the important parts? What are the inputs to the large language model? As we do the demo, we will see this shortly. So one is the system message, obviously. Okay, system message. plus prompt parameters. This is your temperature, the max tokens, all that. Plus user message. User message will come from here, mind you. This is the original user query. So the user message will come from here. I'll write down user message plus the retrieved context. The context will come from here. The context is what is retrieved. So, okay, plus user message plus context. Actually, this whole thing is part of the user message. When I say user message, this whole thing is part of the user message actually. Okay, so this is basically what will go to the LLM as part of the API call. Okay, so you're feeding what is the question the user is asking. You are also feeding to the LLM what is the retrieved context. What is the context we're retrieving? Because the LLM will not answer the question based on its own internal memory. Remember, you can if you go to Chat GPT and if you ask the question that how many leads do I have in a year, GPT model will not be able to answer because GPT model does not have information about your company policy. It will try to take an approximate guess, but it will not be able to give you the correct answer because it doesn't have that information about your company policy particularly. So you will have to give the original user query and you will also have to give the retrieved context. Both will be part of the user message combined with the system message prompt parameters, and that whole thing becomes the prompt. And that is what is be part of the API call, and you get a response. This is a retrieval augmented generation. And if you see, why do we call it a retrieval augmented generation? Because obviously it's a generation problem, very similar to the meeting summarizer, all that we were discussing, but it's an augmented generation. And the augmentation is happening based on retrieval. So first we are retrieving, and then we are augmenting. So first we are retrieving the chunks, and then we are generating the augmented response. It's not a normal GPT response. Normal GPT response would be just where you write a straightforward prompt and get the answer. But this is the augmented response. So as part of the user message, you're giving the input and the retrieve context. And the answer the GPT model is giving is not a normal generation, but it's an augmented generation based on the retrieve context. Okay, so that's what a RAG application basically is. All right, I'm just going to pause here for a minute to understand if all of you are okay, and then we'll see a small demo of this entire thing in action. There are two phases, as you can understand. First part is obviously the vector DB creation, and the second phase is where we actually fine-tune the RAG application, where we fine-tune the system message, the user message, and all that. So there are two phases in the whole RAG workflow. Yes, yes, please. Mm-hmm. Yes. Mm-hmm. Look, I mean, to some extent, there is obviously, see, somewhere there is a risk, agreed. But it's not as if you're sending the whole data as it is in one go. Chunks are very disorganized. And remember, the chunking itself, there are many ways of doing chunking. Now, I gave a simple example here saying that every chunk is a page, but there are different ways you can actually go and do chunking. You can do semantic chunking and all that. So what I'm getting at is if you just see a random chunk, nobody can make any sense out of that anyways. And think of it from OpenAI's perspective. If these chunks are going to OpenAI, you are a huge enterprise. You've got potentially, what do I say, tens of millions of pages worth of documents, right? Now, out of those tens of millions of pages of documents, if one page goes as part of a chunk, as part of a context, nothing will come of that. Now, obviously, there are, I mean, if at all you're still doubtful about the security, then you need to do it open source or, host it on Azure. Anyways, we are using Azure OpenAI. And if at all you're uh, not confident about that, then we have open source models which you have to host locally. So solutions are there, but RAGs are kind of, so it's kind of the best of both worlds. One is you're able to use your own internal company data. And second is you are able to use the GPT model. So one part is the privacy. I'm not saying the privacy and the security is the only part of it. And you're right in saying that, yes, you're still sending the chunks over the open internet. Yeah, agreed. So privacy is not the only idea. So if you really have data security as a top priority in the organization, then obviously you need to do an on-premises open source model. That's one way to do it. So RAGs are kind of the best of both worlds. You are able to use your own company data to make the GPT model answer questions, which otherwise would not have been possible. Think about it that way. Maybe that will clarify better. Because if I go and ask the question, just a minute, if I go and ask the question, how many leaves do I have in a year? Remember, the GPT model is not trained on that. The GPT model is not trained on that question. Uh, so if I just randomly go and ask the question, how many leaves do I have in a year? The GPT model cannot answer that because it is not trained on that data. So the only way to make it work is you need to upload your document on OpenAI servers. You need to upload your document on OpenAI servers, and there are ways to do that. If you want to see very briefly, there are ways to do that. You can actually go to the section called the model catalog, and there is a section called fine tuning, right? So all the models can actually be fine tuned. Unfortunately, it's actually unavailable in our region, but all the models can be fine tuned. So if you go to the model, the GPT-4 Omni, the one that we were using, you can see that this model, beside the deploy, you have a fine tune option, right? So I think in this region, it is not available for fine tuning. You can see a different model. And these models, they all have a fine tuning option also available. If you look at GPT-4, there's a fine tuning option. So if you take a North Central US or Sweden region, there's a fine tuning option. So what you can do is you can click on fine tune, and then you have to upload your data. Upload your data means upload your entire document. And then what will happen is this is a model retraining. So the GPT-4 model is already a very powerful model, which is pre-trained on generic data. So when you upload your document or your data or your files, whatever, now the same GPT-4 model will be fine-tuned based on your data. This is not what we were doing so far. This is extremely expensive. And this is usually the last resort. Until now, what we were doing was we were just using few shot prompting. We were using the meta learning aspect of these LLMs, where we were saying that even without fine tuning the models, just by giving some examples, we are making the LLM do certain things because they are so powerful. But if it's a very different use case, you have to upload your data, and only then the GPT-4 model can answer questions in line with your company's leak policy. There is no other way around that. So RAGs are kind of a middle ground. So on one hand, you are able to some extent, take care of the security part, the privacy part. You are able to maintain your data on premises. You are able to use your own company data. At the same time, you're able to use a very powerful GPT model without fine tuning it. Because otherwise, the only other option is to fine tune, which is an extremely costly proposition. So RAGs are kind of, I would say, a middle ground. Does it answer it? Yeah. Okay, great. Yeah, yeah. There was, yes, Ashok. Yeah. No, 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 no. I just gave an example. You can basically take an entire folder. In that folder, there can be a million documents. Yeah, I mean, anything. Yeah. The chunking will be done for everything combined. Yeah. The vector DBs are huge in size usually. I just say 100 chunks as an example. Vector DBs can be very, very big in size. Yeah. Um, the idea is similar, yes. As I told you, they are processed a little differently. They are processed a little differently. So in short, the answer is yes, you can. Definitely for images, you can do it. But if you think about it, what are videos? Think about it. What are videos? Videos are basically collections of frames, right? Collections of many, many pictures, isn't it? So if let's say you have a 5-second video and every like 30 FPS, we hear these terms, right? 30 FPS, so 30 frames per second. So what is a video? A video is nothing but a collection of pictures, 150 frames. That is how we represent a video. So to answer your question, yes, even if I have a video data, ultimately a video data is a collection of pictures, and that entire video can also be embedded as a sequence of numbers. We can do that. In fact, that is how traditional deep learning models are processing videos, right? If you look at your camera feed, a video feed, a live surveillance feed, how are they processing it? Machines cannot understand unstructured or text, audio, video kind of data. Everything internally is converted to numbers with a pixels. So yes, to answer your question, yes, it's applicable even for video kind of data. We can generate embeddings for that data also. Yeah, yeah. Like for example, I'll just give you, break it technically. Let's say a picture, 100 cross 100 cross 3. If I give you an image will be width cross height cross channels. There are three channels in a picture, right? Let's say RGB. There are three channels. So the dimensions will be 100 cross 100 cross 3 as an example. So images, let's say 3D. Okay, if I say 100 cross 100 cross 3, that's typically the dimensions of a picture. Okay, or we call it 3D tensors, rank 3 tensors. Now, if you go and take a video will be, let's say, 30 cross 100 cross 100 cross 3. So how many pictures? Or let's say 150 cross 100 cross 100 plus. You add one more dimension to it for the frames. So individually, there are 100 cross 100 cross 3 images, right? So I don't know, I think this, and if I write it down, it'll be easier. So every image is, let's say, 100 cross 100 cross 3. And the representation will be somewhat like this, no? So you can have the three channels. The three corresponds to the channels: red channel, green channel, blue channel, and is it a width and height? 100 cross 100 is the width and height. Okay. If you think of a video instead, a video will be 150 cross 100 cross 100 cross 3. So there are 150 such images. Okay. So this is a 5-second video. Okay. I hope the representation is clear. If I take a 5-second video, 30 FPS, so there are 150 frames. So 150 such pictures. So yes, you can embed it also. Yes, there was another question one of you were asking. Yeah. Is this okay? Anything else that anybody wants to ask me? If you're all good, we'll go to the demo. All right. So let us go to the RAG folder once again. And inside the RAG folder, I have the file. There are a lot of demos we have here. And what I will do is I'll start with a very basic one, a very comprehensive demo on a Tesla database, on a Tesla annual reports file. Okay. So what is the use case here? The use case is we will use the Tesla annual report data. So we have the Tesla annual reports. Okay. And you can download. I can show you what this data is. Okay. So let me just download and show you. This is the real Tesla annual reports file. Okay. This is a very, very big PDF file spanning 300, 400 pages. Let me open it up. So there's the Tesla annual reports folder. And you can see that this is how the thing looks like. Excuse me. This is 130 pages. Okay. Annual report. And I want to build a RAG system on top of it. There's so much stuff, right? I mean, imagine like, somebody wants to quickly browse through the annual report and quickly answer questions based on this. Could be very, very useful solutions for investment bankers or financial analysts who look forward to a company's annual report, earnings, revenue guidance. So much of the stock markets and all that are impacted by that. No? So when some company announces something good, the markets go up, go down. So this could be a very, very useful thing that could be used by uh, by companies in a way, and also it could be very useful for even regulators, right? So especially if something is not right in the earnings report or the annual report, it could be a red flag for the regulators. Okay, so things like that. Okay, so now we want to build a RAG application on the basis of this. Oh, excuse me. So this is there are two files I've broken it up into. The first is the indexing file, and the second is the actual RAG file. The two parts we have broken it up into. So first, I will take you through the indexing part. How do we do the index creation? Okay, I hope the rest of the parts are clear. I've already uploaded the slides for you. So here I just talk about the embedding, how do we do the embedding, and this is another similar example of how the whole thing looks like. Okay, so anyways, let me just take you through it now. So we need to connect to a runtime. So just during the vector DB creation, make sure that you go to runtime, change runtime type, and connect to a T4 GPU runtime. This part is important. So because Colab gives you a free virtual machine and it also gives you a free GPU machine. So change runtime type T4 GPU and connect to T4 GPU. See how it's connecting. You can all of you can just observe and then later on you can do the demo. Okay, just observe what I'm doing. So we connect to a T4 GPU runtime and you can actually see what type of runtime is given to you. We get 16 GB of GPU RAM and 13 GB of system RAM, which is a very powerful system. Okay, and it is obviously limited based on your usage. It's not like completely free. Okay, anyways. So now let me install the packages and start with the process. I will also take the Tesla zip annual reports file and upload it here. It will take a while. The one that I downloaded, I'll upload it. Okay. Okay, it is done. I think libraries are still installing. So whatever use case I'm sharing with respect to the Tesla one, you can already think of a gold mine of use cases that you can implement with RAGs. I mean, literally for personal projects, you can take any of your own personal documents. Let's say you have a resume or you have some kind of a health insurance or you have some kind of a bank statement or something. You can literally try out these ideas, whatever files I'm sharing. You can try this out on your own personal data, right? It will be very, very interesting to see. So you can take your PDF, you can replace the file name, you can take something, whatever you want. You take some of your own personal document, maybe 50, 100 pages, you have some data, you can upload that, create chunks, and you can ask questions of your document. Okay, it will be a very fun exercise to do based on our learnings. All right, I think this is still creating. Just wait for a minute. Okay, don't worry about this error. Sometimes what happens is whenever you install some packages, you will have to restart the instance. So if you get this kind of an error, what it means is you will have to restart the runtime. Okay, so go to runtime and say restart runtime. Sorry, restart session. And if you restart the session, everything would be fine. Because when you install something, you need to restart. And after you restart, don't install again. Okay, it's already installed here. This is like a machine. Okay, so if you install a software in a system, you have to restart it. That's what we did. We restarted, then we can import. See, now the error will be gone. Okay, so all good. Now we can. The zip file is also here. So we'll unzip the Tesla report file. So you can see that the Tesla reports are visible here. So we can click on it, expand it, and we can see inside it the PDF folder will be visible. Okay, so now the next part will be chunking. So we'll go and take the file and we will create chunks out of it. And we are using some generic approaches for it. And to load the PDF, we are using something called PyPDF directory loader. Okay, so PyPDF directory loader, what it does is it goes and loads the directory with PDF files. Okay, it loads the directory with PDF files. So inside a folder, there are multiple PDF files. You can have 100, 10, 100,000, whatever number of PDF files you can have in that folder. And the PyPDF directory loader you can just point it to a folder. See how I pointed it to the folder. I said the folder location is Tesla annual reports. This is the relative indexing, relative reference I'm doing. So this is my present working directory, right? Just to show you inside Colab, the PWD, the present working directory is content. So this is the current working directory. So inside the current working directory, with respect to that, I'm taking Tesla annual reports. So we are giving the entire excuse me, the folder name. We're giving the entire folder name, and we are loading the PDF files from the folder, and we are doing chunking. This is the chunking we are doing, and you can actually see how many chunks we created. So we got the chunking takes a little time, maybe few seconds. There are many different chunkers that are there. Now what you can experiment with is you can try to chunk in different ways. So we got 351 chunks. So from that whole PDF file, we are able to get generate total 351 chunks. Okay, and now what I will do is I'll do the vector DB creation. Okay, so I'll take an open source model. So this is the open source model that we are using right now. So there's the GTE large model. Okay, so this is the open source kind of a model that we are using. A GTE large model is what we are using. Okay, so where is it? Where is this list of embedding models present? These are not LLMs, mind you. These are embedding models. So large language models were different. LLMs were different. LLMs are the OpenAI GPT model, the Anthropic Claude model. They are different. So what we are seeing here are embedding models. Okay, so this is different actually. And you can get a list of all these embedding models from the leaderboard. So there's something called an MTEB leaderboard in Hugging Face. This is a massive text embedding leaderboard that you will find. And in this leaderboard, you will see a list of all the different embedding models. Okay, so you'll see that this is the embedding leaderboard, and you will see a list of all the top models available here. Okay, so yeah, so embedding models are different. They are not language models, but these are models that are only used to create embeddings. Embeddings are everything, not only text, images, everything. I told you like there are image embedding models also present. Okay, so can you see image and image only? So there are models that are used only for image embeddings. And look at it, domain specific. There are models that are specific for different domains, medical domain. So if you have a particular text which is in the medical field, you can create an embedding model only for that. So that because what is embedding? Embedding is just taking the text and converting it to numbers, context specific. So now the embedding models are created specific to the context. And say India specific. Indic is regional benchmark, India. And you can see excuse me, you can actually see some of these kinds of benchmarks that are available. Okay, anyways, I think we can actually see the one that we used here, the GTE large model. You can go and maybe search for it, GTE large, and you can see the GTE large model. We'll be able to see here overall. Search for it a little bit down. It might be if you come down. There it is. E5 large, GTE large. This one. It's quite a big one. Quite a big one. 335 million parameters. And see the embedding dimensions are 1024. So the model that we are using, I'll click on it. The GTE large model, it is going to take the data and it will represent the data as a vector of 1024 numbers. 1024 numbers, dimensions. Okay, that is exactly what we are using right now. Okay, GTE large is what we are using. Let me load it. And I will simply create the ChromaDB. So ChromaDB is the open source database that vector DB that we are creating. There are other open source vector DBs also that you can create. You can also use Azure vector DBs, whatever. But idea is the same. But just for the demo, I'm using ChromaDB. So this is how we are setting up the connection. So first we load the embedding model. This takes a little time, and then we define the vector DB. Tesla 10K chunks. You see the Tesla collection will be created. Tesla DB will be created after a while, and then see the Tesla DB is now created, and now the embedding is happening. Based on the embedding model, we're taking all those 351 chunks, and for each of the chunks, we're converting them to the embeddings. And all that is being stored in the vector DB. So that step is happening right now. This is the part that usually takes a little time. That's why I said start the GPUs, because this is the part that usually takes a little time. Because right now we only have 300 chunks, which is nothing. But if you have a bigger document going up to several hundreds of thousands to millions of chunks, this will easily take hours to even days. Okay. So now we can persist the vector DB and we can just test it out. We can just test it out with a few queries, how it works out. We're instantiating the retriever right now. So this is the retriever, and we are specifying that retrieve the top 5 similar chunks. This is where we can give the query. Okay, and just as an example, where do you see the EV sales headed in the next 10 years, right? So this is the question I'm asking, and I want to retrieve the top 5 chunks with respect to the question and see the retriever has retrieved the top 5 chunks. Okay, so this is all happening on premises. Until now, I have not made a single call to my language model. So my vector DB is on premises, and based on the question I'm asking, I'm able to retrieve the top 5 chunks. So these are the top 5 chunks that we are able to retrieve. Okay, based on the content that I have. And now what I will do, the next step will be take that retrieve chunk and send it to the take the top 5 chunks and send it to the uh, excuse me the LLM as the context. Okay. So now what I will do. So this is just my demo. So once you guys do it, what you can do is you can actually continue saving the work along with it. Okay. So now I will go to the next file, which is the retrieval part, the actual RAG part. And see, I'm actually going and saving the work here. So whatever I do here, this is the Tesla DB, right? So what I will do now, I will save my work to my Google Drive. This is a simple piece of code to save my work to my Google Drive. Because right now, what you're seeing is Colab, right? Colab is different, Google Drive is different. They are two different pieces. But what I can do is, whatever files I am taking, see right now, if you remember initially what I did, I manually uploaded the Tesla zip file. But if you can connect to the Google Drive, you don't have to manually upload. You can directly read the files like this. So that is what I will do here. I'll establish a connectivity to my Google Drive. You can just run this code. All this notebook is given to you. So you'll get an option to enable the permissions. You can check all the permissions, permission for all the 8 services. This is like where you're giving Google permission to access, Colab, the Google Colab permission to access your Google Drive. And once you do that, you can see my drive will be mounted. Okay, if I refresh, you will see I will have my Google Drive mounted. This is my personal Google Drive. And within that, I will see all the files. All my personal files will be there in my Google Drive. And what I want to do, I want to copy the Tesla DB folder, whatever the Tesla DB folder I have. Can you see? I want to copy the Tesla DB folder in my current working directory to my this one, Google. Content, drive, my drive, AI, GenAI training. You want to see that? I can show you from here. So content, drive, my drive, you can see right now. So I'm actually saving this here. So I want to take the Tesla DB folder from here. So I want to save it in content, drive, my drive. So this will take you to my drive. That is my Google Drive. Within that, I have a folder called AI, GenAI training main. Within that, generative models. Within that RAG, within that Tesla demo. So within that RAG, within that Tesla demo, you can see the full thing. And within that, I want to save this. Right? I already did that before. But if you run this code, it will just overwrite. See, it is going to save it now. Now we will go ahead and effectively go to the next notebook where we will simply load the vector DB and do the RAG. This is the next part of the demo that we will have. So we'll simply load the vector DB and do our RAG part here. Okay, so that's the next part that we will do. Okay. Now once again, this is a different VM, and here you don't need a GPU because uh, all the processing here will happen in my GPT model. Okay. Using the GPT model, you don't need to use GPUs. Okay, because remember the GPT model is hosted in Azure servers, or if you're accessing through OpenAI, it is hosted in OpenAI servers. So you don't need too much of compute just to access those models. Okay, so those models can be accessed relatively in a simple way. You don't need to use too much of compute to access those models. Not much of compute is required. Anyways, I'm just installing the packages once again. Remember, the first part is done. The vector DB creation is done. You can see my vector DB is already available here. This is what I wanted to show you. So this is my vector DB. It's all available now. Okay, it's all available now. You can see it's modified today. It's all available now. And now I'm just going to use that vector DB. Given a new query, now I will I will retrieve the chunks and give it to my language model and get a more refined response. Because right now the response was not refined. I was just getting those 5 chunks randomly. Now the LLM will give me a refined response. Yeah, yeah. This is my personal drive. No problem. Yeah, you will. I'll keep it. Yes. Otherwise, the machine has no way of processing the data. Whenever you talk about unstructured data like text, images, audio, video, machines don't understand how to process that kind of data. Embedding is done for unstructured data. If I give any text to the machine doesn't understand what is a text. Let's say he is a boy, she is a girl. Machine doesn't understand what is it. So the only way for the machine to understand that is it has to represent that in chunks and understand it. Sorry, embeddings and understand it. Even pictures, images, machines inherently don't understand pictures. The only way to understand images is if it yeah uh, the only way to understand images will be if it is able to uh, you know if we convert it to embeddings. Yeah. uh, no, we will send the query as it is. We will send the query as it is. It will. Yeah, that's what I showed you. Yeah, that's what I showed you. So the embedding will be done by the model. We will not do the embedding. This is the last slide you can see. So when we send the query, this is the the user query. First, it will be sent to the embedding model. The embedding model will automatically generate the query embedding. Based on the query embedding, the chunks will be retrieved. So to answer your question, what are we sending to the LLM? The original user query and the retrieved chunks. The LLM will not see the embeddings. Embeddings are only for the fetching. The LLMs will see the text data. So this will be the text query and this will be the text chunks. Got it? Make sense? Yeah. The retrieval, exactly. The retrieval part. Correct. Yes. Because your GPT model will not understand what those numbers mean anyways, right? Yeah. Okay, great. Let's go back. So we were able to run this. This is the same Azure API key which we said yesterday. This will work fine for everybody. In fact, you can all run this notebook after this demo. So I'll give you time to do that. This is the same stuff. This will run the same way. Load the vector DB. Mind you, we already have the vector DB saved in my location, my Google Drive location. So this is a new VM, right? This was a different VM. This is a different VM. Every time you start a new Colab instance, this is a different VM. This is a different VM. So my files and stuff was not present here, mind you. Okay, so this is a different virtual machine. So I have to make sure that I get my Tesla DB here. So I will load my Tesla DB from my Google Drive. So I already have it in my Google Drive, right? So I will load it from here onto my VM, right? So let's do that. So first I will connect my Colab to my Google Drive. This is in the new VM, mind you. It's a different machine. So I'll establish the connectivity so that my Colab can talk to my drive. Because mind you, Colab is very sensitive. You can write Python code. And literally you can, you can modify, delete, read files. It's very sensitive actually. That's why Colab asks for permissions to ensure that whatever code you run, you are granting it permissions to see and, like change your files. Because it is literally working, interacting with your drive file system. Okay, so once I do this, you can see the Tesla DB will be visible on the left-hand side. And you can see it's available here. Just in case people are doing the demo, I just gave you one more way to work it out. In case you think the Google Drive upload download is too much to take for people, what you can do is I've also given the Tesla DB zip file. I mean, if you think this is difficult or like, anyways, it's not very hard. I'll guide you. But in case you don't want to do this Google Drive way, you can just download my Tesla DB zip. You can download it, and you can just go here and drag and drop it, upload it. That's it. And you can just run this command. I've right now commented it, but you can just run this command. It'll give you the same Tesla DB folder. My objective is to get the Tesla DB folder. Here you created it, and here you want to use it. That's it. They're two separate setups. Okay. So now we define the retriever the same way we define the retriever, top 5 chunks. And now this is the system message for the LLM. So the retriever system message, we are very explicitly stating. Okay. So I want to give all of you a minute here to read the system message. All of you, please read the system message. Give it a read. Let me collapse this section. Read the system message, please. See how we are explicitly stating the question, the context. See how we are explicitly stating that. And also see the prompt template, both the things. The first part and the user message template, the second part. This is all you need. That's it. This is all you need. System message, user message. That's it. This is what we send to the LLM now. Take a minute to read this, all of you. Okay, so you can clearly see we are saying that you're an assistant to a financial services firm. This is the exact use case that we were discussing, who answers users' queries on financial reports. So given the financial report, somebody can quickly query, they can get answers to questions so that analysts can make investment decisions based on the real-time financial reports of companies. And remember, friends, here we are just looking at a single company's financial report, Tesla. But a very, very powerful solution would be you can take all the top 500 companies in the BSE Sensex, the top 500 market capitalization companies, and you can take all their financial reports from the last 10 years. That could be a very powerful solution. And it's not very hard. All this is publicly information. All the publicly traded companies, they publish their annual reports. You have to scrape the data. Just take all the annual reports from the last 10 years. You can save all that data in a folder, and you can build a retrieval augmented generate RAG system, with respect to all the last 10 years uh, financial financial data. Okay, so anybody can ask any question based on any company, and the RAG system will be able to give you answers. It could be very, very powerful idea actually. So, anyways, one very important thing is user input will have the context required by you to answer the user questions. And you can see the context will begin with the token hash 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 context. This is the retrieve context. And the context contains references to the specific portions of a document relevant to the user query. So the context is the one that is retrieved from the vector DB. So you're already telling the LLM that, hey, uh, when you get a question, don't answer the question based on your knowledge. Please answer the question based on the context that we are retrieving. And this is a very, very important aspect of a RAG system. In a RAG system, we don't want to answer questions based on, we don't want the LLM to use its own internal knowledge to answer the questions, but we want the LLM to look at what context is retrieved, and based on the retrieved context, we want it to answer the questions. That is the idea. You can see we're explicitly saying that please answer the questions only using the context provided. Do not mention anything about the context in your final answer, and your response should only contain the answer to the question. This is the part where you're further highlighting the privacy and confidentiality of your documents. So the end users will never get to know the complete document. So this is again very important, right? So you don't want the end users to get to see parts of the document. So only based on the question, the only the answer will be given, but the chunks will not be provided. The context will not be provided in the final answer. Okay. And if the answer is not found in the context, please say I don't know. This is also important because the GPT-4o model is very powerful. It will do whatever it takes to answer the question. Even if you ask it a general question, it will still say, okay, maybe this, maybe that. It will give you some generic answers. But you are very explicitly stating that if the answer is not in the context, please say, I don't know. You are explicitly specifying that. This is the user message template you can see. And now we just test out the RAG system. What is the annual revenue of the company? So first we will retrieve the top 5 chunks. Okay. And this is the top 5 chunks you can see. And now we can compose the response, user input. And this is the LLM call that we are doing. And we can test it out. It takes a minute and says annual revenue of the company is this. This is the part how the RAG system is working. The last part was easy. The last part is what we have been doing already for the last 2 days now. Okay. So once we have the user query, we go to the vector DB. We retrieve the top 5 chunks from the vector DB, and we send the original user question. See, this is the part where we are doing that. We send the original user question and the retrieve chunks as part of the user message, and we get the response. Okay, and this is the final GPT response. It's a much cleaner response. We're not getting those chunks and all those random text that we were seeing before, but now we're getting a very refined answer as you're able to see. Okay, so this is the way how we design RAG systems. The last part is where I will talk a little bit about evaluating a RAG system. Very briefly, I will talk about it. Evaluation part is also very important. So all this while we discussed about how to build a RAG system, but how do we evaluate a RAG system? And there are usually two strategies that are used for evaluation. One is called groundedness, one is called relevance. Now, before that, I want to clarify, there is no ground truth. There is absolutely no ground truth in these kinds of use cases. So here we will use a judge model. So there is no ground truth that we have here. We will use a judge model to evaluate this particular model. So judge model is what will be ultimately used. So what is groundedness? Groundedness means, is the response supported by the retrieved context? So whatever you're responding, is that supported by the context that is retrieved? So the response should not be something random. Whatever answer you are giving, that answer should be based on the context that is retrieved. Very important. Okay. Whatever answer you're giving, the answer should be based on the retrieved context. That is what we refer to as groundedness. The answer should be based on the retrieved context. And this is important because, as I told you, the large language models are very powerful. If you ask it any question, the language models will still do whatever it takes to generate an answer. But that is not what we want. We don't want them to just generate some random answer. Excuse me. We want them to go and answer only based on what they know, not just generate some random answer. So groundedness is an important parameter, and we will use a judge model to evaluate whether the responses are coming from the context and not from somewhere else. And another evaluation metric is something called relevance. So relevance is going to tell you, are we even answering the question? That's also important, right? So you're asking some question and the model will give an answer. Are we even answering that question? So you are saying, okay, what is the annual revenue of Tesla? And the answer is, okay, the profits are this. That is not what I asked. I asked you about the revenue, not the profits. So relevance will do that. How do we do that? We use two judge models. We use LLM1, LLM2. This is the judge model that we use to evaluate. So the first part is we go and use the first language model to generate the response, and we use the second language model, the judge model, to evaluate that response in terms of groundedness and relevance. And that is exactly what we are doing in the last part of our solution. If you see, once we get that final response, we are defining the judge models. This is the same approach that we followed before, right? So these are two judge models, right? So we define the groundedness rater model, and we define the relevance rater model. And this will usually be two separate models, two separate judges, each with its own system message. So we have a separate system message for the groundedness judge and a separate system message for the relevance judge. Obviously, because they are meant to do two different things. The two separate system messages, and you can see what will the judge get as input. The question, the original question that was asked, the context that was retrieved, and the final answer that was given. So three components. First, you have the judge model. The judge will have a system message. Let's say this is the groundedness judge. So the groundedness judge will have a groundedness system message. This is the user message. As part of the user message, we will have the question, the context, and the answer. What was the original question asked? What was the context that was retrieved? Excuse me. And what was the final answer that was given? This will be part of the user message. And you can test it out based on the question. First, the chunks are retrieved. The final answer is given. And now you will send that whole thing to the judge. Can you see? Look at this. This is the groundedness prompt, what the judge will see. So this is the prompt for the judge. Role system message. The system message for the groundedness judge. And role user message. And as part of the user message, see what we have. We have the context. The question. Hashtag question. This is the question. Then we have the retrieved context. And then if you come all the way here, we have the final answer. The final answer actually starts from here, the answer. So this is all part of the user message. The system message is the original system message for the judge. And the user message is basically a combination of the question, the retrieved context, and the answer that was given, the hashtag answer. This is where it's starting from. Answer. The annual revenue was so and so. And you can see the judge model is giving a 5-star because I think the metric was completely followed and the AI's answer is accurate, directly derived from the context. And it does not include any external or fabricated information. This part is very important because a RAG system must answer questions based on the context, based on my company's data for accuracy. The accuracy part is very important. You just don't want the LLM to answer the question, but it also has to be accurate based on my company data, not based on GPT's own understanding. Okay, so this is how we look at a complete end-to-end use case of a RAG system.